basıyorum. Tamam.
Siz de Sayın Hocam. İyi çalışmalar.
Recording permission. Please request recording permission from the meeting host diyor. Ankara, I'm not the host. Just a minute.
I will wait. When you tell me, I will share my screen.
Okay, that's better. Just a minute. Let me write to the organizer that okay. I should be able to record this session, but because I'm not exactly the host, I cannot press on the button. So if I press the button, it says I need to request a permission from the host. So I just wrote to the organizer that
Okay.
I can be transferred as a host, so I can start recording this session.
Sure. Very nice to see you after a long time.
Thank you.
Sayın Hocam hostsunuz şu anda.
Ama burada host görünmüyor. Bir dakika. Evet. Ha, record on this computer. Tamam. Şimdi oldu. Şimdi geldi. Süper. Tamam. Thank you very much. It was very. I was very happy that I met you in India, and it was, you know, we were like friends for years, and you know, I wish we didn't have the pandemic problem.
Yes,
and we could be you know, wandering around in Ankara in the streets, and it would be. I'm very happy to host you here as well. Hopefully, next time we are organizing a conference, we will be able to host you, and we can visit few places in Turkey as well.
Yeah, I look forward to that.
Yes, thank you. Now I think I have to start this session. You are the first speaker in this session, and you are invited speaker. Let me introduce you to the YouTube viewers. Professor Rahul Mitra. I'm honored to say that he is a very good friend of mine, and he is from Department of Metallurgical and Materials Engineering from India Institute of Technology, Kharagpur. And his topic or his subject will be on creep and oxidation behavior of zirconium diboride and silicon carbide based ultra-high temperature ceramic composites. And stage is yours, Professor. We are listening to you.
Okay, thank you. Good afternoon. So I really thank the organizers, particularly Professor Sukru, Professor Talas, and Professor Hates for inviting me to this prestigious conference. Unfortunately, I'm not able to visit Turkey, which I really wanted to because of the pandemic. Hopefully, I'll get another chance, as pointed out by Professor Talas. So we are working on the GW2 SiC based ultra-high temperature ceramic composites for last 15 years. So I will give you a glimpse of recent results that we have got with a little bit of past results to tell us the total story about the creep and oxidation behavior of GW2 SiC composites, whatever we have achieved in our laboratory. My students, Mr. Sunil Kashyap, who is my present PhD student, has mainly contributed to this work. And my earlier PhD student, who is now a professor at National Institute of Technology, Durgapur, he also, part of his work also I'll be presenting towards the end. So we are from IIT Kharagpur. I'll just briefly tell you where we belong to. So you can see that we are in the eastern part of India. So this is India, this is the state of West Bengal, and this is Calcutta, the capital of British India. And after the British left, the government of India decided to set up 5 Indian Institutes of Technology, and IIT Kharagpur was the first one, and the largest and the most diversified of all IITs. This is IIT Kharagpur main building, and Kharagpur is about 150 kilometers from Kolkata airport. This is our department, Metallurgical and Materials Engineering. This is my research group, and this is Sunil Kashyap. The picture is slightly distorted. It was a selfie taken by Sunil. He's good at that, and he's the main contributor for this work as well. So I'll be talking about I'll briefly introduce the subject, and then first I'll cover the effect of lanthanum hexaboride addition, which is basically an way to add rare earth element lanthanum along with boron, so that the densification, oxidation resistance, and creep resistance could be improved. So this material was processed by spectral sintering. We added 7, 10, and 14 volume percent of lanthanum hexaboride. And we have studied oxidation and creep behavior. And creep behavior has been studied between the range of 1300 and 1400 degrees centigrade. Oxidation behavior in the range of 1300 to 1500 degrees centigrade. And silicon nitride 5 volume percent has been added to ZrB2 SiC composite. Oxidation behavior has been studied in the range of 1200 to 1300 degrees centigrade, and compressive creep behavior between 1300 to 1450 degrees centigrade. Finally, I'll summarize each part of the talk, and I will give some concluding remarks at the end. So why we work on ultra high temperature ceramic composites? These have very high melting points, and the main interest went for work on these composites because of their possibility of their use in nose cones and thermal protection tiles and leading agents of re-entry vehicles in hypersonic flight vehicles. And also there are possible applications in aero engines because of their high temperature capability, furnace heating elements, and arc plasma electrodes. So these are some pictures of where they could be applied, and they are being applied to some extent. And these are the properties of ZrB2. Besides ZrB2, HFB2 is also of interest. But HFB2 you can see is heavier. So that way ZrB2 is better off. And they have also reasonably high flexural strength. The hardness is very high, more than 20 GPa. Elastic modulus is also high. One disadvantage is poor fracture toughness. So obviously, to some extent, we can improve by addition of other reinforcements. But at the same time, we cannot compromise on the high temperature properties too much. Pure ZrB2 and pure HFB2 has poor oxidation resistance beyond some temperature like 900 or 1000 degrees centigrade. So silicon carbide is added as a reinforcement so that a borosilicate glass SiC will oxidize to form SiO2, and ZrB2 forms the B2O3. And B2O3 of ZrB2 and SiO2 from SiC, they add together from a borosilicate glass, which is protective in nature. However, there are problems regarding densification of ZrB2 because pure ZrB2 has low ionic diffusivity at elevated temperature. It is covalently bonded ceramic. The presence of oxide impurities such as ZrO2 and B2O3 on particles surfaces hinders densification. And also high processing temperature causes grain coarsening and degradation of mechanical properties. So these are some problems. And it has been observed that if you add silicon carbide, about 20 volume percent, it helps in densification. We have another publication from there. I am not going to talk about it today. And many other people have also seen, but besides that, certain other additives are also required. The problem with ZrB2 is that first of all, it is covalently bonded, and then it has these oxides like ZrB2 and B2O3 on the surfaces. These have to be reduced by adding some kind of additives. And also during processing, you get grain coarsening. So to take care of some of that problem, silicon carbide, when it is added, it actually inhibits grain growth in ZrB2. And we have also added lanthanum hexaboride here. We will see that it acts as a scavenger for oxygen when the processing takes place. And besides, boron carbide and carbon have been also added. These are also additives to scavenge the oxygen so that densification is promoted. Here the processing was done by spark process sintering. The use of spark process sintering actually lowers the processing temperature and high temperature hold time during the sintering process to 5 to 7 minutes, which actually lowers the possibility of grain growth. At the same time, densification is achieved under pressure. So the spark process sintering was done at 1800 degrees centigrade, and we got good density. These are 7, 10, and 14 volume percent lanthanum hexaboride composites. This one is an etched micrograph where you can see the grain boundaries and silicon carbide particles more clearly. And we could discover ZrB2, SiC, and boron carbide by EDS analysis. Uh, this is a this view graph shows the microstructures obtained at 1600 degrees centigrade. I mean, by doing spark process sintering at 1600 degrees centigrade. These also show that all the phases are well distributed, and silicon carbide and boron carbide, they are basically located at the grain boundaries of ZrB2, as expected. We did X-ray diffraction studies, and although the pre-sintered powders showed lanthanum hexaboride peaks, the post-sintered powders, after sintering, we found that lanthanum hexaboride was not there. I mean, of course, it may be there, but the amount was low, and a good part of it converted to lanthanum borate, BO3, because it was acting as a scavenger for oxygen. Of course, ZrB2 and SiC were there. And this view graph shows an evidence of the formation of lanthanum boron oxygen, lanthanum borate. And this was confirmed by ACM as well as by TEM, and we did STEM EDS, and we could see this as lanthanum borate. Again, this is at the ZrB2 SiC interface, triple point. So lanthanum hexaboride acts as an oxygen gator and forms lanthanum borate. In this way, it actually promotes by taking away the oxygen, consuming the B2O3, it actually helps in the sinterability or densification, the ability to densify for ZrB2 SiC composites. And we found that the relative density actually scales with the lanthanum hexaboride content. You can see that as we increase the lanthanum hexaboride content from 7 to 14 volume percent, relative density has increased. Here, in the case of 1800 degrees centigrade, it has increased from 95 to 98.2. And of course, the grain sizes are more or less comparable, with some of those little smaller, like if you have more lanthanum hexaboride, even at high temperature, you could get little finer grain size. So let us see now our other properties. Now you can see this is hardness. Hardness is again is higher for the 14 volume percent LAV6 composite. And for 7 and 10, difference is not much significant. But we got a significant increase in hardness on addition of 14 volume percent lanthanum hexaboride. This is again due to better density achieved. And we also found there is a correlation with grain size. Normally hardness, based on Hall-Page relation, hardness should increase with decrease in grain size. And that kind of behavior you could observe at for relative densities greater than 97.5%. We looked at the non-isostomal oxidation behavior. For this study, the samples are kept in a thermogrammetric analyzer and heated at the rate of 5 degrees centigrade per minute, from 25 degrees centigrade to 1400 degrees centigrade in air. And all the three composites here begin to oxidize at the same temperature. You can see more or less at the same temperature, there is an increase in the mass gain. And the ZSBCl 14 composite shows the highest mass gain, as you can see here, followed by the ZSBCl 7 and then 10. So this is for non-isotomal oxidation, where we do continuous heating up to 1400 degrees centigrade. So here the ZSBCl 14 is the worst when you are doing continuous heating. Then we did isothermal oxidation study at 1300 degrees centigrade. So this is the mass change behavior at 1300 degrees centigrade. You can see this is the work done at 1 hour, for 1 hour. Here you don't see any kind of trend. There is a lot of fluctuation. And after 8 hours, I mean, when we do the experiment for 8 hours at 1300 degree, we could see a trend emerged, and there is some kind of a parabolic behavior. And ZSBCl 7 shows the highest mass gain, and ZSBCl 10 shows the lowest mass gain. And ZSBCl 14 shows, which is the 14 volume plus LB6 composite, shows somewhere in between. When the duration of experiment was 24 hours, and result and mass gain was measured at every hour, we saw that the ZSBCl 14 shows total flattening of the curve beyond some time, and the mass gain is, the net mass gain is the least after 24 hours, followed by ZSBCl 10 and followed by ZSBCl 7. So here you see that if you increase the lanthanum hexavoid content, we are gaining by reducing the mass gain and lowering, so improving the oxidation resistance. So this is something which we have published in Journal of European Ceramic Society recently. And so we want to know what is actually going on. So we have identified the phases formed in oxide scale by X-ray diffraction. And we found that the ZrO2 and lanthanum oxide and lanthanum silicate have formed. And this is true for all three. Of course, ZrSiO4 has also formed after 8 hours and 24 hours. Lanthanum oxide is no more there after 8 hours or 24 hours, but after 1 hour it was there. So we have summarized whatever our observations in the text over here. So let us see the kinetics. So we looked at the parabolic kinetics.
Do you mind if I ask one question?
Yeah, sure.
Okay. In the previous page, can you go up one more pages?
Yeah, this one.
Oh, okay. Oh, one more up. Sorry.
One more. Okay.
Yeah. In this in 24 hours and 8 hours,
Yeah.
that ZSBCl 10 and 14 is that 14 performs a lot better just after 10 hours, isn't it?
Yes, we have looked at that also. So we have analyzed that result little later. We will be able to see that. This is when I talk about kinetics.
Okay.
So,
okay. Sorry.
Yeah. Before that, there was it was different. So if you look at the kinetics, actually, particularly parabolic kinetics, we have also found out the n value by plotting. I'm not given the equation, and I forgot to do that. It is delta Wn is equal to kT plus C. That is shown here, and we found the n value. So n value greater than 2 means smaller. The rate, the oxidation kinetics is lower than parabolic. Higher n value, it is better. Then these two view graphs are actually for that, and these two are actually for the parabolic rate constant. So you can see the parabolic rate constant is the lowest for the ZSBCl 14 composite, and it takes a turn beyond certain about 8 hours or so, and the slope changes. So there is a change in the mechanism also that shows.
Oh, yeah.
And here the slope is changing or all of them. So there is a change in the mechanism. So between 0 to 8 and then 8 to 24. So that is something which we have actually looked at. And this is the variation from a parabolic rate. We have just used this equation to find out the rate of mass change, variation rate of mass change with time. We have plotted d delta W by dt. And this is coming at kp by 2 delta W. So from here we have plotted this variation of rate of mass change with time, with and hours. The stability coming before that, actually it is decreasing continuously. After that it becomes kind of stable, and obviously the 14 volume percent composite lowest rate of change of mass gain, followed by the other two composites. You can see for 1 hour, 8 hour, and 24 hours. So the oxidation products are, after 1 hour, are porous oxide scale of ZrO2 plus borosilicate glass, which is formed here. This is unoxidized composite. After 8 hours and 24 hours, what we get is a top layer of lanthanum silicate followed by SiO2 B2O3, which is called as borosilicate. Then there is a next layer of zirconium oxide, SiO2 and B2O3, which we call BSG, porous ZrO2 plus BSG, and then there is an unoxidized composite. Now this is true for both 8 hours and 24 hours. That evolves after 8 hours continues to be there, only the relative thickness has changed. So we have also monitored the thickness after 8 hours and 24 hours, also measured for 1 hour. Our assessment is that so growth of BSG layer is significant in the first 8 hours. You can see that it has grown to 12, 17, or 27 in the first 8 hours. But between 8 hours and 24 hours, the growth is much smaller. From 27, this has gone only up to 31. And if you consider error, hardly there is any growth. Only what we are taking the average. On the other hand, for 7 and 10 volume percent, there is some amount of growth compared to 14. So the growth rate is also reduced with increasing lanthanum hexaboride content. And the total oxide scale thickness after 1 hour, ZSBCl7 shows the best result, and ZSBCl14 shows the worst result, maximum oxide scale thickness, which also was observed due to non-oxidation and non-isomal behavior. When we did continuous heating, ZSBCl14 showed the highest mass gain also. So in initial period, ZSBCl14 actually shows the worst kind of mass gain. But after some time, the trend is totally reversed. So having higher lanthanum hexaboride content is actually beneficial because it is helping in the formation of protective scale. And once the scale forms, the stable regime is achieved, and that takes about 8 hours, 8 to 10 hours or so. So that's what we found also. We plotted the BSG layer growth up to 8 hours and versus lanthanum hexaboride content, and we see that it increases as we increase the lanthanum hexaboride content. But as you beyond 8 hours, actually it decreases with increasing lanthanum hexaboride content. So this is one interesting result that we found out from this study. And another interesting result that we found, we correlated the BSG layer thickness and parabolic rate constant. You can see that BSG layer thickness, because the thicker it is, it actually is acting as a diffusion barrier, that it increases the diffusion distance for oxygen, oxidizing species as well as oxygen. As a result, the thicker the BSG layer, less is the parabolic rate constant. So basically its growth actually helps in reducing the rate of oxidation. And that is seen between 0 to 8 hours and also between 8 to 24 hours for all the three materials. So that there is a direct correlation between the oxide scale layer of BSG and the kinetics that we are getting out of mass change. So this was a Nobel contribution from this work, and we have published it.
Yes.
Next, we'll talk about oxidation in the range of 1300 to 1500 degrees centigrade. So this paper we have not yet published, but it is under consideration. So this is here we can see the mass gain behavior at apps showing basically we have exposed at not only 1400, it should be 1400, 1500 and 1300 for 24 hours. Also, so we can see that at each temperature, the mass gain, actually mass change decreases as we increase the lanthanum hexaboride content. There is a sharp increase in the mass gain between 1300 to 1400. 1400 is a slight decrease in the total mass gain for each of the composites. So what is going on? So this is something to be looked at. Which shows the X-ray diffraction patterns for 1400 degree centigrade, 1 hour, 24 hour, and 1500 degree, 24 hour. We can see that all of them show the formation of zirconium dioxide, which is monoclinic zirconium dioxide, and lanthanum silicate. So these are forming, and we have then looked at the top surface. Now here we see a trend. If you go from the 7 to 14 voluminous lanthanum hexaboride composite, you see that roughness is decreasing and also the porosity content is decreasing. That means having more lanthanum hexaboride, we get a more coherent and smooth and stable scale. So, which actually helps in reducing the mass changes and oxidation rate. So this is the mechanism which is operating. So this is something which we see, we qualitatively determine by looking at the oxide scale. And then we have looked at the cross section. So here also we see layers. Now here, unlike the one at 1300 degrees centigrade, we see one fine layer of, this is again at 1400 degree, we see a fine J2 plus borosilicate glass, and then lanthanum silicate plus borosilicate glass. At higher temperature, when you expose for longer duration like 24 hour at 1400, 1500, besides fine J2 and borosilicate, we also see coarse J2 layer. And as we increase the temperature, the coarse J2 layer actually increases in thickness. With, of course, this is mixed with borosilicate glass.
Okay.
So here it's, and so we have actually looked at the EDS maps and determined the composition of those layers. The top layer is lanthanum silicate, followed by borosilicate glass and J2, which is coarse, and then of course, see, this is we have shown this as a here. The composition is similar, so we we have not differentiated between fine and coarse. Then there is a silicon depleted region where actually the layer is porous, and where fine J2 is actually there. And then there is unoxidized composite. So this is seen in all the individual X-ray maps for zirconium, silicon, oxygen, boron, and lanthanum. You see that outermost layer is lanthanum silicate.
Is there any,
so the possible reactions?
Is there any explanation why silicon is depleted in that region?
Yeah. Because there the silicon carbide is getting there is low partial pressure oxygen, so there is some active oxidation of silicon. So that leads to formation of SiO and CO. So if there is passive oxidation, if there is SiO2 is forming, then it will not be depleted in silicon. But because there is active oxidation, and it is always happening at a lower, you can see that it is happening at an underneath layer, not at the top surface. And that is because this oxygen partial pressure is very high here, but inside oxygen partial pressure is decreased. So there is active oxidation of SiC.
So instead of
actually is predicted also.
But
and we have looked at the thermodynamics. Yes.
Nothing happens to zirconium though.
Zirconium forms J2. So J2 cannot vaporize, but SiO vaporizes. This is a gas, so it basically leaves porosities. So we have J2, and so we get the porous layer of J2 there. And this is happening at all three temperatures: 1300, 1400, 1500. It is less at 1300, but more at higher temperatures, like 1500 degree. You can see that the delta G becomes more negative with increasing temperature.
That's true.
Of course, there is more possibility of formation of SiO2 over here Thermodynamically, it is more favored, but at a lower oxygen partial pressure, this reaction becomes more favorable
Mm.
because SiO2 is not converted to SiO2. It remains as SiO, which is a gas.
Right. Okay.
And then lanthanum silicate, you can see that its formation energy is very negative. So it is forming ZrOCO4 is also forming to some extent.
Yeah. Very negative.
And
Yes.
then we have looked at the thickness of oxide scales. Now here also we can see that the initially we have only BSG plus ZrO2 after 1 hour, but after 24 hours, both at 1400 1500, we have a coarse ZrO2 plus BSG and fine ZrO plus BSG layer. And as we increase the temperature, the thickness of the coarse BSG layer actually increases. Another interesting phenomena that we have observed that the net mass gain in 24 hours is inversely proportional to the thickness of the fine ZrO2 plus BSG layer. You can see this actually. So the material with a more amount of fine BSG,
Yeah.
ZrO2 plus BSG, is showing more mass gain and more total thickness. So basically, there is more grain boundary area. If you have fine ZrO2 plus BSG, there is more grain boundary area between ZrO2, and that actually acts as short circuit path for diffusion of oxygen. So that way, and it is actually better to have a coarse ZrO2, so you have less grain boundary area, and it is more protective.
That's interesting.
Then we have also looked at oxide scale using TEM. We made samples by focused ion beam, and we have found that there is a dispersion of nano-size lanthanum silicate precipitates and also sub-micrometer ZrO2 precipitates, which are observed over here. And these are the diffraction
Very fun.
patterns confirming their formation. Then we have looked at the creep behavior of these composites. I have just given the compositions once again so that it is easy to recall. So we have 7 and 10 and 14 volume percent added to ZrB220 SiC composite. All of them had these additives and they are prepared by surface sintering. These are the pre-creep microstructures or composites prepared at 1800 degrees centigrade. You can see that in the ZSBCl 14 composite, we have a lot of dislocations. Dislocation jogs and
very
tangles are there. But in the ZSBCl 10, the dislocation density was low, and we could see some kind of very arrays, but overall density was low. And at the triple points where there was a glassy phase, which is confirmed from the diffuse halo over here. In some grains there are dislocations, but other grains didn't have any dislocations. So during surface sintering, we apply pressure, so that leads to some kind of a creep, which I've analyzed, but I'm not showing it here. But it actually creates dislocation formation due to when the intergranular glassy phase is not there. When intergranular glassy phase is there, because of that, actually dislocations are not formed in the grains. So ZSBCl 10, which had more intergranular glassy phase, because it has less amount of lanthanum hexaboride, actually it doesn't show that much of dislocation density. And this is another view graph showing twins in silicon carbide and dislocations in ZrB2. And this is the diffraction pattern from ZrB2. And this is pre-creep microstructure from ZSBCl 10 composite. You can see that we have lanthanum borate or glassy phase at intergrain triple point, and we can see glassy phase conformation. So because of that, dislocations are rarely found in the ZrB2 grains of ZSBCl 10.
Is there any
Compression
effect of
creep-
these glassy phases? What sort of
It is
effect are you
actually
expecting?
some kind of because of SiO2 and B2O3 both being present, it forms borosilicate glass, and it may have some lanthanum also in it. So it could be a complex lanthanum silicon boron or even zirconium. So we have not really analyzed the composition of this glass, but we have seen that in the oxide scale such kind of glass forms. And this is creep testing machine, compression creep testing machine. The sample is kept here. This is a silicon carbide push rod, and we have silicon carbide RAM. Extensometer is also here, and we have an LVDT below, and we put it's a lever arm tester. So and it is loaded from this side, and by lever arm mechanism, the sample is loaded in compression. It is supplied by ATS from USA. And the compression creep results look like this. This is a strain versus time plots, and you can see there is a primary creep regime which is followed by the secondary or steady state creep. There is no tertiary creep because the work has been done in compression. And from we have looked at the creep rates or the steady state creep rates, and from there we have measured the stress exponents, and we have found the stress exponents by plotting log strain rate versus log stress. And we have found for the JSBCL 14 composite, the stress exponent is around 2.6 and around 3. And for the 10 JSBCL 10 composite, the stress exponent is about 1. And we have written the grain sizes also over here. And this is compared with the hot pressed composite. I will show a little bit more results about the hot pressed composite, which has shown superior creep resistance because of coarser grain size. And these are the JSBCL 10 composites showing interfacial cracks, particularly cracks are more near the surface. And we could see an oxide scale of ZrSiO4, lanthanum silicate formation, and ZrO2 and SiO2. And near the oxide's top surface, near the surface, we could see more intergranular cavities formed. So that shows that glassy scale actually penetrates inside the ZrB2 SiC. And what happens is that glassy phase becomes soft at high temperature and permits grain boundary sliding and some kind of a diffusion creep. So it plays an active role in diffusion creep. So this is the behavior at 1300 degrees centigrade. We analyzed the oxide scale formed using EDS mapping, and we have seen formation of lanthanum zirconate also and lanthanum silicate as layers. You can see as and this is shown here, the top layer being lanthanum zirconate and silicate, followed by ZrSiO4 and ZrO2 plus SiO2 plus SiC, then SiO2. And this is the formation of interfacial microcracking. So that shows that grain boundary sliding to some extent is operative in these materials. And also there is deformation of the ZrB2 grains because already dislocations are present. And this, because stress exponent is around 3, it should be dislocation glide control creep, but some amount of sliding is also there. Whereas in ZSBCL 10, sliding is the main active taking place, and its grain size is coarser. So it has shown slightly better creep resistance than ZSBCL 14 composite. And that you can see if I scroll back, you can see that the creep resistance, the creep rates are actually lower for the ZSBCL 10 composite compared to ZSBCL 14. We have measured the oxide scale thickness, and we have found that the total thickness, if you is less than 10%, even after 12 hours of creep. With creep, oxidation is taking place. So we have measured oxide scale thickness after the total creep test. And obviously the duration of exposure is different. But one interesting result that we found that if we expose a sample to isothermal oxidation at 1300 degrees centigrade, without applying the load that we are doing in creep, in that case, the oxide scale thickness was lower compared to that what we get under compression creep condition. So under compression creep condition, we are applying a compressive stress which actually breaks open the oxide scale and permits further oxidation. On the other hand, in the case of isothermal oxidation without any load, the oxide scale can form and it is not damaged. So that is one advantage that we are getting. And that is why the oxide scale thickness that is emerging out of the experiment is less. So, but another interesting phenomenon that we have observed is that oxide scale is more adherent and protective in the ZSBCL 14 due to formation of lanthanum zirconate and lanthanum silicate as a continuous layer, which is not forming in the ZSBCL 10. But ZSBCL 10, because of its coarser grain size, is showing better creep resistance here at 1300. We found with little more investigation that lot of dislocations, less number of dislocations in ZSBCL 10, but interfacial cracks and glassy phase, showing that grain boundary sliding plays a major role, and also N is 1, the stress exponent is 1. On the other hand, in the ZSBCl 14 composites, we could see a lot of dislocations, dislocation pile up and micro crack inside the grain, indicating that also at the grain boundaries at times. So indicating that there is plastic deformation taking place, and because these are basically partly ionic bonded, partly covalent bonded solids, dislocation movement is slow in this ZRB2. And but intergrain sliding here may be taking place, which we have seen evidence for, and but it is accommodated by dislocation slip, not by diffusion. Whereas in the case of ZSBCl 10, it is accommodated by diffusion because of the glassy phase. And we get intergranular cracking also. So to summarize the effect of lanthanum hexaboride on creep, the relative density and hardness values of ZRB2 SiC composites increase with increasing lanthanum hexaboride. And we found that beyond 97% density, grain size affects the hardness. And values of stress exponents as well as examination of post-creep microstructure size dislocation, glide control, deformation to be operative in ZSBCl 14, and diffusion control creep to be operative in ZSBCl 10. Creep resistance of ZSBCl 10 is found to be superior to that of ZSBCl 14. Presence of glassy phase at grain boundaries in sintered ZSBCl 10 may be responsible for lack of dislocation slip. And formation of cracks at ZRB2 grain boundaries of ZRB2 suggests that grain boundary sliding is the major operative mechanism. And coarser grain size of ZSBCl 10 actually has helped it in better creep resistance. So we have also looked at the creep behavior at between 1400 to 1300 to 1400 degrees centigrade, and we found that, and this we have seen for looked at for ZSBCl 14 composite only. So this view graph actually represents ZSBCl 14, and it has been seen that the stress exponent is again 1 at between 30 here. Now here actually we have used a composite which was sintered at 1600 degrees centigrade. Here the stress exponent, unlike that in 1800 centigrade, is equal to 1, and activation energy is coming like 667. So we have to still analyze the reason for why this kind of activation energy is coming. We are looking at the behavior. So looking at that n equal to 1, it should be diffusion creep, and because of probably the formation of lanthanum zirconium, a complex glass, probably the oxygen diffusivity is reduced, and so that is why we get a high activation energy. I will show you the results that we have got for ZSBCl for silicon nitride added zirconium silicon carbide composite, and for that activation energies were lower. So stress exponents and activation energy is summarized here for ZSBCl 14 composite in this table. So again, this has been already told, so I need not repeat it. So now we'll look at the effect of silicon nitride additions on ZRB220 SiC composites. These composites are prepared by hot pressing at 2000 degrees centigrade, and we are looking at ZRB220 volume percent silicon carbide, another one with 5 volume percent silicon nitride added at the expense of ZRB2, and this is the hot pressed compact. These are about 99% plus density, relative density, almost full density is there. Silicon nitride was found to be more at the interfaces, ZRB2 SiC triple points, and these are, of course, these show very good distribution. And we found that at room temperature, the grain sizes are comparable, and at room temperature, silicon nitride addition is very beneficial for getting a higher Vickers hardness, higher flexural strength, also higher fracture toughness. So silicon nitride appears to be very good for this purpose, and it gives us the best combination of room temperature mechanical properties. Then we looked at the oxidation behavior. Both at 1200 and 1300 degrees centigrade, if we have 5 volumes of silicon nitride added in the place of ZRB2, it actually helps in improving the oxidation resistance. The mass gains are found to be lower, and for the silicon nitride composites having silicon nitride, you can see from this mass change versus time, both at 1200 and 1300 degrees centigrade. And this is the oxide scale that is formed. You can see for having composites having silicon nitride have more smooth, less porosity, etc. And we found that if it's silicon nitride is there, Si2N2O is also formed in oxide scale, which actually is helping in improving the coherence and the density of the oxide scale that is forming. We looked at the creep behavior. Now here it is opposite. You see the creep rates for the silicon nitride composites having silicon nitride is ZSS is higher at all temperatures from 1300 to 1425 degrees centigrade. The N value varies from 1.7 to 1.1. But silicon nitride composites, silicon voluminous 21 silicon nitride 5 voluminous silicon nitride composites, we see that the stress exponent becomes less than 1. Now this was something very fishy. Also, if you look at the activation energy, we have plotted log strain rate versus 1 by temperature, absolute temperature, using that Arrhenius relation between creep rate and temperature. So if you see the slope, from the slope we have measured the activation energy. The activation energy is higher below some temperature, and activation energy is lower below some temperature like 1350 degrees centigrade. It is 95 plus minus 32. Above 1350 it grows to 470 plus minus 20. So it is higher, but it is less than what we got for ZSBC L composites. And then we have determined the oxidation, we have compared the results with activation energy for oxygen diffusion, and we have found that diffusion of oxygen ions through glass actually accommodates grain boundary sliding, and this activation energy that we got is somewhat close to the activation energy for diffusion of oxygen ions through the glass, SiO2 glass. And this activation energy that we have found around 450 or so, this is equal to the activation energy for viscoelastic flow of intergranular glassy film. So this is quite high at this temperature. Obviously, if you in the case of lanthanum hexaboride, because we have lanthanum addition, so this viscoplastic oxide scale is probably more viscous and activation energy is higher. So this is something which we are working on at the moment. And then we have looked at the thickness of oxide scales, and we have again seen that the net oxide scale thickness as a ratio of initial oxide specimen thickness was less than 10%. So the oxidation taking place during creep test did not affect the creep test results much. This analysis was done because the reviewer asked us to do so, because when the oxide scale when the sample is being consumed by oxide scale formation, obviously to some extent it affects the creep results. So that is why we determined oxide scale thickness and as a fraction of the net specimen thickness. Of course, there is change in the volume also, because some of these oxides actually lead to volume expansion.
Oxide thicknesses are lower in this one, I think.
Yes, it is lower. So silicon nitride actually helps in the improving the oxidation resistance. Here you see that this is exposed to 36 hours and this is exposed to 26 hours.
Oh, I see.
So that is longer duration also.
That's true.
And then we looked at the oxide scale composition, and we found ZrO2 and SiO2 formed. And we also saw near the interface, near the oxide scale, there are intergranular cracks or interfacial cracks, showing that there is a possibility of grain boundary sliding during creep. And we have again looked at in the TEM, and we have seen formation of intergranular glassy phase, which is confirmed from the diffuse halo around the central spot, and also cracking at the grain boundaries. In the case of ZrB2 SiC, silicon nitride composite, we also found formation of Si2N2O. You may remember that the stress exponents are found to be less than 1 here. We also found evidence of intergranular cracking. And so we've found that in the case of silicon nitride composites, actually this Si2N2O forms, and there is a kind of solution reprecipitation type of mechanism, which actually leads to stress exponent less than 1 in silicon nitride ceramics. So there is formation of Si2N2O by oxidation of Si3N4, and the solution of Si2N2O in the liquid phase at grain boundaries, and it diffuses to the grain boundary this species, and then it reprecipitates as Si2N2O at grain boundary triple points. So that's how actually we find this kind of Si2N2O formation, and that is actually responsible for deformation contributes to deformation and stress exponent values less than 1. And we have also looked at activation volumes using this kind of relation, which is activation volume is given by NKT by sigma at a constant temperature. And what we have seen is that the activation volumes at lower temperature and stress is equal to volume of 2 silicon oxynitride tetrahedral is reasonable for diffusion of oxygen ions, which accommodates grain boundary sliding. At higher temperature and stress, we found that it is equivalent to displacement of which is equivalent to displacement comparable to lattice constants of SiO2 or Si2N2O. So that involves viscoplastic flow of intergranular glassy phase. So this is another way of confirming that the mechanisms that we looked at, we are saying through our analysis of activation energy and stress exponent is also confirmed by your examination of activation volume. So summarize the effect of silicon nitride on creep. Addition of 5 volume silicon nitride enhances room temperature strength and modulus, but lowers the improves the oxidation resistance also at high temperature, but lowers high temperature creep resistance. The stress exponents are found to be in the range of between 1 and 2 for zircon diver silicon carbide composites. And for certain temperature range above 1400, we have found it to be less than 1 for composites having silicon nitride. And post-creep microstructure shows evidence of cracking at particle matrix interfaces and grain boundary, which actually indicates that is grain boundary sliding or interfacial sliding taking place. And n less than 1 for silicon nitride containing composites is attributed to formation of Si2O2O, is their dissolution and reprecipitation. Activation energies also shows evidence of defined mechanisms like diffusion controlled creep with oxygen diffusing through glassy scale controlling the rate of creep at temperatures less than 1350. At higher temperatures, actually, it is the viscoplastic flow at high temperature which is rate controlling. And activation volumes also lead to similar results, which is summarized here. So some concluding remarks, I would like to add that effect of silicon nitride and lanthanum hexaboride has been studied, and creep behavior is strongly affected by oxidation and ingress of oxygen aiding in formation of intergranular glassy phase. So if normally all these components are supposed to be subjected to creep or loading at in the atmosphere and air. So if the test is done in vacuum, then the effect of oxidation is lost. So we have tried our best to see the effect of oxidation on creep behavior and formation of oxide scale during creep. Both lanthanum hexaboride and silicon nitride aid in improving the oxidation resistance. It is actually obviously better oxidation resistance, creep resistance also should improve, but we see that silicon nitride, because of silicon nitride, that doesn't happen because it has a different kind of creep mechanism. Even 5 volume silicon nitride has lowered the creep resistance. But in the case of lanthanum hexaboride, the results are slightly different. It doesn't really lowers the creep resistance, it improves. We have seen that adding 10 or 14 volume percent lanthanum hexaboride, actually creep resistance improved. And grain boundary sliding and diffusion creep are predominant in these composites, except at 1300 degrees for ZSB cell 14, where you could see dislocation creep because intergranular glassy phase was not there and it had dislocations to begin with. So that is another thing. But the creep mechanisms can change. Obviously, it depends on the temperature. If dislocations are there, formed during the processing. So that end comes to so we come to the end of this presentation, and I thank you for your kind attention.
Well, thank you very much, Professor. It was very intense and very informative. Thank you very much for your presentation again. I'm just checking if there is any question with viewers from YouTube and Zoom as well. It seems we don't have any questions, but it's interesting that the mechanisms are it's quite different. But what I noticed, as the surface porosity lessens, it's better. It becomes better, the oxidation resistance.
Right. At least for the oxidation resistance, if the oxide scales are coherent and less porous, it is better for oxidation resistance as well as for creep resistance.
Why did you do compressive creep? I mean, is there any reason for compressive creep?
Yeah, these materials, first of all, in spark plug sintering or hot pressing, we get basically plates. So it is not possible
Oh,
to
I
take out
see.
tensile samples. And number two is that these are very brittle materials. So in tensile creep, it is not possible to judge also, because there may be flaws, and it may just break even just while loading the sample. So that is why we are interested in getting the steady state creep results rather than in tertiary creep. So we have done compression creep. Normally for ceramics, intermetallics, a lot of people do compression creep.
I see.
And they are not supposed to be used under tension. At the most, somebody can do bending creep. So that is something which you can target in future. In flexure creep test can be studied.
Okay. But at high temperature, sometimes you expect to, you expect to have some carrying capacity or load carrying capacity. I guess in this case, there is no such requirement.
Right.
I see.
Yeah, not that much of a requirement. So creep is actually, for the kind of applications that I've shown in the very beginning, creep is not that important. But if you use this in aero engine, then obviously creep becomes important, depending on where you are using. And it is not definitely for turbine blades, but some components where you can use at high temperature, maybe high, like nozzles or exhaust or height, or any other point where there's some high temperature is there, so where you need thermal protection. So there it is can be used, but there are other issues like weldability, that so, and also retaining the high temperature capability. All those things are there, which is under development.
Is there any application, or have you done any work with this material in terms of joining to metals?
Joining, yeah, some work is there. Even in India, some people have worked on it. Now we have a project where we have to do joining to refractory metals and like niobium, etc. So we have to try that out.
Oh, okay. The other oxides also possible, I guess, joining to
Right.
other oxide
Joining to other
materials.
ceramics also
Ceramics.
is of interest.
Yeah. Okay, thank you very much for your very good presentation. And I'm just checking if there is any other.
Sayın hocam,
Efendim.
söz hakkı istiyorum.
Yes.
Diğer hocalarımızın CD'leri mi var, yoksa kullanamadılar mı?
Bir sonraki hocamızın şeyi var. Neydi?
Birisi.
Videosu var. Evet.
Tamam. Tamam Sayın hocam. Ben o zaman şey yapayım.
Videosunu başlatacağım.
Çünkü ben şey zannettim. Linkten mi ulaşamadılar diye.
Şimdi başlatıyorum o zaman.
Tamam. Sağ olun hocam. Teşekkür ediyorum.
Right. Our next guest of invited speaker is Mina Lad. Just a minute. I shouldn't say anything different. Mina Lad. She's a professor from Symbiosis Institute of Technology. Let me check straight away. She was not able to join this to present her presentation, and we have a video, and we will play the video of Mina Lad, Professor Mina Lad. She's, as I said, she is from Symbiosis Institute of Technology from Pune, India. I'll play the video that she has submitted. Tamam.
The food for them, they were used to be weapons to save and protect them from the animals.
Tamam, baştan başlatayım şeyi. Tamam.
It's my pleasure to and addressing all of you today. I'm really thankful to the organizing committee and especially Professor Happen who gave the opportunity to come and speak to you. Thank you very much. Today I thought that as we all are researchers working in the area of science, why not we take a review of the journey of material and come to a common platform where we all find out in what way we can cooperate and can help each other in our research pursuits. So I will be talking about the journey of materials, where we started and where we are today, and what are the future opportunities, especially in India, and I think that the problems that I have taken are common worldwide. Okay? Let me take you through my presentation. So, once again,
Geliyor mu?
welcome to my presentation, and my topic is materials, the challenges and opportunities.
Oh.
And you can see that I'm professor in physics from Voices International University.
Tamam.
I want to tell you something about my university. It's a beautiful university in Pune, the state of Maharashtra, and basically my university caters to international students. There are students from more than 75 countries, and I'll be showing you that there are a number of faculties that we are having. This is a lovely view. It is situated at hilltop and greenery all around. And here also you can see a bird's eye view for my university. We at Symbiosis have education right from KG to PhD, and we have 49 academic institutions. There are 20 campuses located around India, and 30,000 students are on campus, and global representation from 85 different countries. Then we have several faculties. We have Faculty of Management, Law, Computer Studies, Media, Communication and Design, Health and Biomedical Sciences, Humanities and Social Sciences, Engineering, and also we have started recently with Faculty of Sports, as well as we have Culinary Arts. This is my institute. It is also situated in a lovely lush green hill base, as we call it, and it's a lovely institute. So now I start with the historical background of materials. As you know that in pre-3000 BC, we were having Stone Age. All the brittle materials used to make earthenware, tools, and weapons. So it is more out of the requirements, necessity during that time to protect themselves from the animals around or to cook the food. So they were using the stone. So that age, Stone Age materials or stones were used for making the food for them. They were used to be making weapons to save and protect them from the animals. So tools allowed hominids to become the masters of their environments, to hunt, to build, and to perform important tasks that made life easier for them. So we can all understand that the basic material used was stone. Then came Bronze Age materials. In this era, the humans started making objects from metals such as gold, silver, and copper. They made alloy of copper and tin called bronze, which allowed much stronger and more durable tools to be produced. So you can see that the stone is brittle in character, you know that. So they graduated with their own research. They could find and discover one alloy, which they called as bronze, which is a mixture of copper and tin. They could find that the weapons that they were making they were much better. So after Bronze Age followed Iron Age. During the early Iron Age, artifacts were made from iron found in meteorites. So you can imagine that by the time they didn't have that digging out from the mines and extracting iron. But from the meteorites that were falling on the earth, they could find out, they could extract iron and make their weapons. The tools were hard, tough, ductile, and cheap. They were used to make sophisticated tools, bridges, ships, etc. So you can see that the social life or economic life was also graduating along with the development of materials. So early metallurgists found that very small addition of carbon to iron combined with heat treatment led to massive increase in strength. So from stone, which was not as strong, which was more brittle, they graduated to bronze, and from bronze, they graduated to iron, which was comparatively cheaper. The tools were hard and tough as well. And as you can see here, that this is the first cast iron bridge built over the river Severn at Holbrookdale, that is in UK, in 1781. So that was the material. You can understand the importance of materials, because how important for the mobility, for connecting people from two ends, how important bridges are there for transportation, for developing economy. So that was made with the advent of iron, with the discovery of iron. The first bridge was made in 1781. Then came Roman age. Wood, bone, stone, and ores from the earth were the materials used in Roman age, and also discovery of lead and other ores which were then used for roofing, building ornaments, water pipes, and coffins. So you can see here that with the development of materials, the social life, economic life also was affected, and it was moving towards growth. Then it was followed by industrial revolution age. The rapid industrial growth was because of use of coke, another material you can see, a carbonious material produced from coal in blast furnace, the iron making. Using this multifunctional material significantly lower production cost and enabled increase in production volume. So cost does matter. So with all these, as the materials were being discovered, the strength was something which was looked for, and also it should go hand in hand with the reasonable cost. So industrial revolution happened because they discovered coke, which was a kind of carbonious material, and it could be used for large volumes of goods to be produced. And today, 1915 AD until today, we are working in silicon age. You know that discovery of germanium silicon has revolutionized our life. The silicon microchip is the advancement that made the modern computers era possible. The ability to create a miniature circuit board out of a semiconductor was what gave computers vast advancement in speed and accuracy and compactness. It is whatever the new technologies that we are having, the sleek mobile phones that we are having. We talk about IoT today, Internet of Things, modern super fast computers, quantum dot televisions, very multifunctional mobile phones, all are possible only because of the silicon. So today we are in silicon age, and we do not know when you are going, where we are going to progress next. What will be the new revolutionizing materials, which of course I will be considering in my subsequent slides, the future materials as well. So now we start with traditional materials. Now wood, metals, horn, bone, rope, enchantment, skin, which is parchment is nothing but the skin of sheep, goat, etc. Tools and a host of other materials, all of which would have been familiar to craftsmen from 50 to 500 years ago. So you can see we used to have wood, then we were having horns, like this, and the ornaments they were using, making tools and ornaments and other artifacts. But today, if you see, depending upon the functionality, depending upon the cost of the materials, these modern materials and the artifacts made by these are very expensive, and you can find only in some emporiums as well, or big hotels you can see. But otherwise, we have progressed a lot. So today's materials, we call them advanced materials. You talk about silicon, you talk about nanomaterials or superconducting materials. There are variety of smart materials, shape memory alloys. All these materials are called as advanced materials. So what are advanced materials? Is it a new concept, or we were having it right from the beginning? So typically either traditional materials whose properties have been enhanced or newly developed. And these are high performing materials or advanced materials. They are used in high-tech applications such as computers, fiber optic systems, spacecraft, aircraft, and military rocketry, you name it. And we are using the advanced composite materials. But is it a new concept? No. Answer is no. 4000 BC also, you could see that there are proofs that laminated writing material from papyrus plant, it did exist, that advanced composite material did exist in 4000 BC. 1300 BC, Egyptian and Mesopotamian used straw bricks, you can see here, right? This is writing material, this is the straw bricks, and here in 1200 AD, Mongols invented the first composite bow plates back to 3000. Here you can see. So why do we need the advanced material? Because we can have desired or customized properties, improved properties. And what are those properties which are expected from the materials that we synthesize? These are strength, stiffness, toughness, corrosion resistance, wear resistance, reduced weight, thermal, electrical, acoustic insulation, energy dissipation, attractiveness, cost, availability, customized properties. These are the basic things that we expect from a material, depending upon, of course, the requirement, what are the applications that we have. So I will be discussing about the composite material. My research area is synthesis of composite materials. So I'll be sharing that with you. Based on matrix materials, but what are composite materials? You can see here a material which is composed of two or more materials at a microscopic scale and have chemically distinct phases, right? So if I'm making a composite material of, say, some ceramic and some metal, so when I make a composite material, then the composite, which is formed by mixing the two, mixing is the not right word, with these two materials, where say metal is the matrix, the larger component, and the silicon, what I have used, silicon dioxide, which normally I'm working on, if I use, then the material which is formed has entirely different chemical properties than either the metal that I have used as matrix and the reinforcement silicon dioxide that I have used. And what I could observe, and you will see that in composite materials, the properties are enhanced. It will be better than the metal that I have used. It will be better than the reinforcement that I have used. So these are the composite materials. Constituent materials have significantly different properties. So based on what metrics that you take, you divide basically into three categories: metal matrix, ceramic matrix, and polymer matrix. So the larger component is, it could be metal, ceramic, polymer, and then reinforcement could be from anything. It could be a particulate reinforced composite, it could be viscous flakes reinforced composite, and fiber reinforced composite. So we can make the materials, advanced materials, which are composite materials, using any of these metrics materials, and then we could see that the material, the composite which we have formed, is having enhanced properties. So 4 essential elements in material science and engineering. When we work in materials, what are the important things that we all look for? I'm sure it will be very helpful for the researchers who are interested to come into material science, and also the postgraduate students who intend to do some project in material science. So basically, we need processing, synthesis, what the right method of synthesis. Then we go for structure and composition. We make study. There are advanced characterization techniques to understand the surface morphology, to understand the structure. So XRD, EDX, ACM, TEM, these are all the techniques that we use. And then once we synthesize the material, then we look for the properties, right? So if suppose I want to make a material, metal matrix composite, I have aluminum as the matrix, and I'm using silicon dioxide or silicon carbide as the reinforcement material, and I want to use that for some synthesis or some product for, say, inner lining of some engine. So what I'm going to look for, I will be looking for the strength, right? Tensile strength and all compression strength of that material, so that it can withstand that much amount of stress. So depending upon what is the application where you want to use your material, you study the properties. So now you can see here that when and which material matrix for making that composite material, what should be the metrics that I use. So if you are looking for, say, high tensile strength, high stiffness, high fracture toughness, this kind of properties, go for polymer matrix composite. But one thing we must remember that also the operating temperature makes a lot of effect on the properties. So which temperature range you want to use your material, that is equally important. So in my next slide, I am going to show you the operating temperature for these. But polymer matrix composites are used, as you can see, these are the properties. You can use this. These are some of the examples that we are commonly using in our day-to-day life: epoxies, phenolics, the pipe, and the other plastic material that you are seeing. Low density polymerethylene, high density polythene is so common, high density. You can see here some of the applications: sports, biomedical equipment, electrical insulating, toy making. Everywhere you can see that there are a lot of applications of these polymer matrix composites in our day-to-day life. Then, if you want your material for some high temperature capabilities, 800 and above, then you use metal as matrix. You can see metals have this good quality, their high temperature capability, fire resistant, high transfer stiffness and strength, no moisture absorption, higher electrical thermal conductivity, and better radiation resistance. So depends. You must, before going for your research, you will find out what is the application for which you are synthesizing your material, and then you can go for that. Ceramic matrix, you know that they're highly dielectric insulating materials as far as conduction of electricity is concerned. So high thermal shock resistance, high temperature resistance, excellent resistance to corrosion and wear, and inertness to aggressive chemicals, high tensile and compression strength. So these are the properties of these materials, and you can see the respective applications here. You can see these are the materials for the different machining parts. You use the metal matrix composites. Here you can use silica-based, alumina-based, silica-based composites, and applications are heat exchanger, turbine-based, high-performance materials. Here, as I mentioned, that the temperature, operating temperature, and in which temperature range you're going to use these materials, that's very important. So you can see if you are having a polymer matrix composite, the temperature range is somewhere around 400 to 500. Yeah. So if this is your operating temperature, you can use safely polymer matrix. Then metal matrix composite, you can see it goes up to somewhere below, somewhere around 1200 degrees C. So go for this. If you want the ceramic matrix, they still have higher operating temperature, somewhere around 1500 degrees C. And there is one carbon composite, which are very newly entered in this material composition or composite materials. And we are having the temperature range. It's not only very strong mechanically, but also it has operating temperature range of 2000. So what I mean to say, why did I show you this slide? Because I want to let you know that depending upon your application, you have to be selecting the materials for as the reinforcement and material as the matrix. Now, what is my basic aim to speak about materials is to network with people, to know about the research that the worldwide going on in this area, and where we can pitch in and work together. So these are some current opportunities and potential where we can actually work together, and a lot many opportunities for research are existing today. Renewable energy. Every country needs this energy. And more we are using electronic gadgets, and we know that the energy sources, conventional energy sources are exhausting, right? We do not have enough petroleum, diesel, wood, coal, and we have to look for alternate sources of energy, and those ones which are renewables. This is one area where materials are the basic units for any product. So we need to have those kind of smart, efficient materials. Second application, healthcare. If you see the way diseases are happening, you can see the way COVID has changed our lives, isn't it? So how to go for antibacterial coatings or antibacterial materials or other health applications, the vaccines, you name it. And there are a number of applications for healthcare. And as you know that the number of aged population in the world is increasing. And by a survey, I got to know that by 2026, there will be more than 173 million people only in India having age 60 and above. So you can imagine how much infrastructural changes are required, how much healthcare applications are required. So this is one important sector where there's a lot of opportunities for research. Then electrical energy. Whatever energy that we are generating is not sufficient. And even when you generate, the storage is not that good. We need storage applications. We need different kind of very efficient batteries when we talk about unmanned vehicles today, right? Then or modern ways of transportation, then we need batteries. So a lot of work is to be done as far as energy storage as well as energy conduction opportunities are concerned. Then modern transportation. As I mentioned, unmanned vehicles are there, hybrid cars are there, fast moving cars are there, the smart trains are there, flights, the aircrafts are there where we are using fiber optics and aluminum. We need a lot of material research for this, even the spacecraft, space applications. There is a lot of scope for developing new materials which are just right for the application. Now, sustainability of materials is so important. We all know that what menace that plastic has created. It's not biodegradable. So we want materials in such a way which are biodegradable, which are not causing any harm to aquatic life or to the environment, to the animal life. So we need to take care of sustainability of the materials as well. So energy future, let's a bit about each area. Battery materials for massive electrical energy storage, high efficiency and low cost solar cells, corrosion resistance alloy for high temperature power conversion, strong lightweight composites for turbine blades, superconducting power distribution cables, advanced power handling electronics, and so many other. These are some of the areas which I could think of. So especially the researchers, the young researchers who want to get into this kind of material science research, please bear in mind there are so many problems in hand. You can pick up anyone and start working on it. Then modern transportation, you can see our first one, the earlier one was steam engine, and you can see how we are today. We are today at a hydrogen PM fuel cell car, fastest moving cars, unmanned cars. You can see here a lot many sensors are there, which are sensing with there is some property which responds to whatever stimulants are happening. So here you can see that lot many opportunities for developing sensor materials for these smart materials that we are having, smart cars that we are having, improved. So in this area, where you can work, improving combustion efficiencies, batteries for electric and hybrid vehicles, fuel cells, hydrogen storage, new tire compounds and manufacturing processes, biofuel production, and more. So you can see that even in modern transportation, there are many opportunities to work for research. Healthcare, naturally derived biodegradable polymer materials for drug delivery. Drug delivery is so important. So we need this biocompatible, mechanically strong materials for implant, be it a dental implant, be it a bone implant, hip implant, we talk about. But if the material is not strong, then there will be problems. If the materials are corroding, then there will be problems. If the material is not compatible to our human bodies, then also there is a problem, right? So we look for some materials which are used with a biocompatible, having good mechanical strength and can be used for in human bodies. Biosensors for early detection of diabetes, cancer, CVD, and other such diseases. You pick up any research paper and you will get to know that in almost every country, these diseases have spread like anything. The number is increasing. People are getting more and more prone to these diseases, and there are so many deaths happening every year in every country. So in what way we can protect? If we develop some materials which can diagnose it early, and then necessary precautions or treatment can be taken, we can save so many human lives. So you can see biosensors, huge potential for development. More and more COVID, we can work on that. In COVID, how to protect ourselves from this kind of COVID, right? Viruses. Then protection for clothing, protection clothing, which do not absorb liquid or moisture. So the racers or the athletes or the people working in the mine, always there is some risk to their lives. So if we can provide some kind of electronic clothing which can early detect any kind of accidents, then this will be a great help, isn't it? So there are, you can see some of the pictures that I have seen, which not very good quality, but just to make you understand, nanofiber based face masks with thermal management. So you can see that when nowadays when we are wearing face masks when we go out and meet people to maintain the social distancing and protect ourselves from corona, it's sometimes because if you're running or you're jogging and you're wearing that mask, it becomes very difficult because that it generates heat because of our breathing and we find it difficult. So if we have some thermally sensitive mask, then it will be really good for everyone. Then we have clothing and personalized heating and cooling. You can have something depending upon your body type. You can have that. Then we have heatable gloves, right, which can withstand temperature and accordingly they can maintain their temperature. Then thermal regulation textile. So whatever material that we are using, in every country has different climate. If I go to Europe, then it's too chill for me. If you come to India, you will say it is too hot. So can we have some kind of thermal regulation textile, and especially for sports people or the people who are working in very, very cold areas, or for our defense people, we can think of these applications. Then stretchable feature, stretch triggered. So there are so many opportunities for advanced materials for renewable energy, materials that are abundant, non-toxic, low carbon. Materials are available, but what materials that we are looking for, or what should be the aim for our researchers, that they should be easily available. I just want to give you an example. For example, this space applications, when we develop materials, the problem is applications are limited. Every now and then, everybody is not making the aircrafts. So the materials are limited, right? So if we want to go for any application, we should get the materials easily. It should not be very restricted, that the availability is not there. You're not finding it in the market. It should be available. Then non-toxic. When we are talking about the pollution-free environment, and we know with the increase in this industrial growth, environment is getting polluted, isn't it? So we have to look for non-toxic materials. Then cost does matter. If you are using it, as I told you, that way advent of coke, the industrial growth could take place. Same way, we want the materials which should be easily affordable. Then developing novel nanoscale surfaces to reduce reflection and increase capture of the full spectrum of sunlight. We are not able to capture the full spectrum. Even our best efficient solar cells are also somewhere the efficiency 17% or so. So a lot of scope to work in these areas. Extending the lifetime of photovoltaic systems, or you know that this is a problem area. Reducing manufacturing costs and creating efficient high volume methods to recycle solar system materials. Inexpensive plastic solar cells or panels that are mounted on curved surfaces. You must have observed that we are using solar cells on flat surfaces. What about the curved surfaces? We need it there also to maximize our energy, right? Energy is saving. So we need that kind of panels as well. Unique forms of PV driven by the imagination of material scientists, silicon nanowires, nanotubes, flexible plastic organic transparent cells, ultra thin silicon wafer. Silicon is used almost everywhere. So for this wonderful material, we should have it. As you can see, we are talking about modern cities, modern infrastructures, smart cities. So energy efficiency becomes very, very important. In India, you know that our government is coming out with few smart cities. So energy, there's a lot of scope in developing energy efficient buildings. So what kind of buildings? Low emissivity glass, significantly lowering the initial investment cost for heating and cooling, compact fluorescent lighting and light emitting diodes, reducing lighting costs and heat loads, cool roofs, saving energy, high efficiency fiberglass insulation, phase change materials. very novel materials, phase change materials, where during the phase transition, that energy transfer is there. We can utilize that one, or storing or releasing large amounts of energy in the walls, floor and roof, thereby saving energy and smoothing the thermal profile. So you can see that everywhere materials find the applications with the industrial growth, with the social growth, with the growth in economy. All these things have become so important. The research in material science has taken front line place. Materials for sustainability. We all are living and we deserve, we have a right to have clean air. We should have clean drinking water, clean environment. So lot of things to be done in this area. The greatest challenge for material scientists and engineers is to design, develop, and commercialize recycle-friendly materials, products, and systems. Why we ban plastics? In many of the countries, plastics are banned because not biodegradable and also it is not recycled, right? It is so toxic that you cannot use it further. So we need to work in these areas too. Some of the modern wonder materials that I'm showing here, you all know, liquid crystal display, different pictures of liquid crystal change color at different temperature, you can see here. So if you're using it as a band, and nowadays, because of COVID, you go to any airport, office, even in my office, we have thermal screening. So we can use this. Some innovative devices you can think about it. That liquid crystals, they change colors with different temperatures. So if you want to protect yourself, you can have this kind of band. And if you see your temperature is not within this range, you can take immediate measures. Then LEDs. These are the metal foam. Metal foam is having very good strength like metals, but at the same time, it's like foam. The density is extremely small. So the applications where you need the strength, but at the same time, very lightweight, definitely you can go for. And when we talk about space applications, where the strength is very important, at the same time, the weight is also to be controlled. You can have this kind of metal foams. So here you can see an LED woven in textile. So this is a very good application. You can think of several such applications. Titanium, which is used for implants in our body. An excellent material with high strength to weight ratio, resistant to corrosion. So you can see in most of the implants, titanium is used. This is again another use of LED woven in the textile. And here, a single, this one is graphene, wonder material, single carbon layer material, hypothetically 100 times stronger than steel. And this is memory wire. The girl is wearing these braces, and when the stress is there, if you go for old wires, braces, then they will break, they will be, the shape will be changed. But this NITI memory wire, will, after the stress is removed, it's original shape. So you can think of that these are important applications of these materials. We talk about nanometer, nanoparticles. All of you are aware of this. And Richard Feynman in 1960 gave this. There is plenty of room at the bottom. And here are the nanomaterials. So nano effect is something important here. This is Richard Feynman, the father of nanotechnology. And what is important that as we reduce the size and dimension, if there are tremendous change in the properties of the material, then that nano effect is something that we can use for making wonderful materials. So you can see atom having size 0.1 nanometer, CD, SE nanoparticle 5 nanometer, then a red blood cells 8,000. This is just to give you a grain of salt, 100,000 nanometer, right? So just to give you an idea about how much is nanometer. Nano effect is that at certain size range, the impact of size on the property is dramatically significant. The value of that property significantly changes. It could be in terms of strength, it could be in terms of optical properties, magnetic properties. So if these properties drastically change with the reduction in size to nano level, then that is nano effect. Due to this, the same material with new set of values can now be used for newer applications. That is interesting. So once you know that as I reduce the size from bulk to nano, and this property is changing, then you can use many in different materials. So realization, what are those? Realization of miniature devices with more functionality, attainment of high surface to volume ratio, manifestation of novel phenomena and properties, including changes in physical properties, chemical properties, electrical, mechanical, and optical properties. So key areas of nanotechnology are healthcare, as we discussed, agriculture, water and air filtration, transportation, food technology, construction, electronics, endless applications. So keeping in mind, we can continue our research. Now I will talk about futuristic. These are the materials we have. We are working. Of course, we are not working in as many applications possible, but we are working futuristic materials that I'm going to talk about now, which we recently started, and it is not in vogue, it is not common. So quantum dots. These are 3D semiconductor structures, only nanometers in size, confining electrons and holes. By making dots of different sizes, one can create light of different colors. If you have seen this quantum dot TV, and if you compare it to your normal plasma TV or digital TV, you will see that there is a huge difference in the clarity, the colors, efficiency. So quantum dots is a very new thing. A lot of research opportunity exists. Ferrofluids, colloidal liquids made of nanoscale ferromagnetic or perimagnetic particles suspended in a carrier fluid, usually an organic solvent or water. These ferrofluids are used. You can see beautiful pictures here. These are ferrofluids. Some of my students in their BTech degree, they did one project and they created the braking system in vehicles using the ferrofluids, right? So not many opportunities for in ferrofluids. Metamaterials. These are artificially crafted composite materials that derive their properties from internal microstructure rather than chemical composition found in natural materials. So you can design, right? You can make these materials. See, this is one metamaterial. You can design these materials, and you know that as you are designing the material, they're changing their internal structure, then you can have the different properties of these materials. So these are metamaterials. Then transparent aluminum, very interesting. Can you see this? Aluminum, you know that, how hard it is, silvery, but this is transparent aluminum. So aluminum oxynitride or alon, as it is marketed, is a transparent material made by placing aluminum powder under immense pressure and polishing it to produce a glass-like. It's a very light yet very strong material. Isn't it a beautiful innovation? So wherever you need a material, for example, our windows or the glass windows or our windows at home, or what you say, the screen, sheet screen in our cars, vehicles, you can use that. It is transparent, and at the same time, it is not as brittle as our glass which we are using. So a lot of applications. Then e-textile, sometimes called smart garments or smart clothes, are fabrics that have electronic woven into them. So when the players are there, or our traffic police, when they are working at night, you can have these textile materials. Aerogel, sometimes called frozen smoke, is a unique material that consists of 99.8% empty space, making it look semi-transparent. Despite its low density, aerogel has incredible insulating properties. So, especially for space applications where weight matters a lot, you can use, and if for applications where you want the insulating properties, then carbon nanotube. So wonderful, wonderful material. Carbon nanotube consists of long chain of carbon held together with strong double covalent bonds. The type of bonds found in carbon nanotube are even stronger than similar carbon bonds found in diamonds. You know that diamond is the hardest material found in nature, but till date, that was our understanding. But carbon nanotubes are having even stronger bond, and we can use it. And you'll be surprised that that what we call as Damascus swords, the material was imported from India. And that time they were using carbon nanotubes extracted from plants long back. And they were using, they didn't know that this is a nano-sized material, nano-sized carbon, they didn't know about it. And in different proportions, they were using that. But because of their strength, India was exporting, especially the South India was exporting that material to India. And because the design is called as Damascus design, that's why the swords are called Damascus swords. But nanotechnology did exist long back. Then next is artificial spider silk. This spider silk has incredible properties with a tensile strength that is higher than steel and a woven matrix. that is tougher than Kevlar, but synthesizing it has been a challenge. So can you imagine the silk that we go for, silk that we use for furnishing the clothes and can we create that artificial, very strong silk? So this is where a lot of research is still going on. Molecular superglue, scientists at the University of Oxford have created a new kind of superglue from a flesh-eating bacteria that bonds at the molecular level. The new glue offers numerous applications, including encapsulation of electronics and developing better water tight. So wherever you need, you see that when you join two things because of water, because of stress, they just get detached. We need some kind of super glue. And a lot of work is going on in this in Oxford University. So where do we need these materials? We are talking about futuristic technologies. Not many inventions are happening. We are looking forward as far as technology is concerned. What are the opportunities? Bioplastics. We need materials for bioplastics. Social robots, as I said, that elderly population is increasing. To help them, to support them, we need robots, we need machines. So when we develop machines, it has to have a lot many sensors. So when we are using sensors, obviously, it zeroes down to the new material, development of new materials. So opportunities, tiny lenses for miniature devices. One area untouched, we can do wonders here. Disordered protein as drug targets, as biophysics, you can work in this area. Smarter fertilization to reduce environmental contamination. India is a country which is dominated by mainly agriculture. So we definitely need research, advanced food tracking and packaging. And you know that nowadays, especially during COVID times, majority of people are going for online shopping. Imagine for transporting food, then you need a definite type of food packaging. So a lot of scope is there for food tracking and packaging, safer nuclear reactions, DNA data storage. These are another areas where a lot of research is required. So I want to tell you about myself, research, what am I doing? I have received research grants from national and international agencies for my work. It is Defense Research and Development Organization. They have given me grant for synthesis of nanolubricant with less pollution. So I'm working on that. Then University Grants Commission and Department of Atomic Energy is another national agency who has supported me for synthesis and characterization of metal matrix composites by green route, where I extract silicon dioxide from the plants. So that's my other research grant that I have received. I have also received a grant from British Council that is called as UKRE, UK India Education and Research. In this, my partner university is Aston University from UK, where 20 students from Aston University, along with 2 professors from Aston, will be coming to my university for some training. So because they were supposed to come in this December, but because of COVID, we have postponed it to June 21. Then I have recently received the Duo India Professor Fellowship with University of Leeds. I have my partner, academic collaborator from University of Leeds, Dr. Girish, and this fellowship, which is given by Government of India, supports my going to University of Leeds and work in my research with my academic partner in University of Leeds for 1 month. So this is what I have received. I have authored several research papers and also authored books which are published by high-level databases such as Science Citation Index, Springer, and Scopus. Then I'm a PhD supervisor, and these are my students. Sunil has already done his PhD in intermetallic compounds. It is awarded. Deepa is working on pavement materials, and she is going to submit. Rinku is working on my UGCDA project. Vishal is working on my DRDO project. Babaji is working on supercapacitors. Anuradha working on super hydrophobic coatings. Hemant is working on nanofluids. So this is how in varied areas my research scholars are working, and these are the current areas: composite materials, intermetallic compounds and their properties, nanomodified pavement materials, nanomodified lubricants. just a glimpse of each project. This is, that this rice husk, okay, and we are taking rice husk from this, centering it in the furnace. You can see here the temperature is up to 100 and till 1000 degrees C. This is how it becomes, and then using acid lynching, we are extracting nanosilica, and this is crystalline silica. So transition is from this rice husk to silica, nanosilica, and then with reinforcement using metals as matrix. This is copper, aluminium, titanium, and using this silicon dioxide as what we extracted from green root as reinforcement. These are the materials. These are composite materials which we characterize further for their properties and use them in different industrial applications. So this is one project. Then Deepa is working on nano-modified pavement materials. If you go to countries, which are tropical countries, very high temperature, then this rutting of roads you can see, right? Fatigue. You can see a lot of potholes are there, cracking is there, melting is there. So Deepa is working where she has taken bitumen and then modified it with some additive materials, nanomaterials, which are polymers, bio waste, industrial waste. And then after completing basic engineering tests that it will include softening point, penetration value, viscosity, elastic recovery, she has gone for these advanced tests as well. And she's coming out with some new construction, low cost material, which is very environment friendly. This is my student Sunil's work, where he worked with electric, magnetic, and lattice properties and their interplay in R3ALCX system. R stands for the rare earth elements. They are also extremely good materials, but very less research has happened so far. If you take R3AL, if you take only the rare earth with the metals, then, and if you add little bit of carbon in the range of 0, 0.25, 0.5 to 1, you see that there are huge changes in the properties of these materials, and they can use at various applications. So my research scholar who has received the PhD on this work has worked on these systems, and you can see here that the various properties that he has studied, the electric, magnetic, temperature dependence, other magnetic properties, susceptibility, all these he has studied and could observe that with little amount of carbon, he used melting art method for forming this, for synthesizing these RTLCS systems, and all studied properties in detail. And these properties can be used for magnetic storage of devices, data storage devices. So this is all about my work, and I'm very glad that I could address all of you, and I'll be very happy to receive your queries, and I can, at this time, I'm feeling really sorry that my experience with Turkey has been wonderful. Last year, I attended one conference in Ukraine, and I met Professor Hakan and other my colleagues in the conference, and it was such a wonderful experience to be there. So this time I'm not there, but I welcome all your queries. I am very happy if I can collaborate with you all and work together. Research, here is my email, and I thank you so much for giving me support. Thank you. God bless you. Have a great time.
We have another video from Professor Mina Lat. Now we will play that video. This video is basically on the work or study she did or she prepared for this presentation.
Hello dear audience, good morning. Hello dear audience, good morning. My name is Rinku Datkile. I am project fellow working under the supervision of Dr. Meena Lat. I stand here to deliver this presentation. So title of this presentation is Synthesis and Characterization of Copper Metal Matrix Composite Reinforced with Ceramic Oxide Extracted by the Green Root. Keywords is powder metallurgy, metal matrix composite, silica, rice husk ash, XRD, copper metal composite. Abstract is the overall preview of this presentation. In this study, powder metallurgy was used to fabricate metal matrix composite. Silica as a reinforcement has average particle size is 45 micrometer. Then the structural and chemical properties were investigated. Various characterization technique was used like XRD, then EDS, energy dispersive X-ray spectrum, and then scanning electron microscopy. Let us see introduction part. So metal matrix composite is a multi-element material. It has unique property than the individual element. This composite have wide application in the field of engineering. And the powder metallurgy and green chemistry route method was employed for the composite preparation. In solid waste, rice husk was used as a precursor in the overall process. Finally, the prepared specimen was characterized by various sophisticated techniques. That is the X-ray diffraction, which is use Bruker D8 advanced with copper alpha with lambda is equal to 0.154 nanometer wavelength, and the scanning electron microscopy equipped with energy dispersive X-ray liquid nitrogen cooled EDS detector. Material used in the study is first one is this is the rice husk ash. So figure 1 shows the rice husk ash. It was procured from a local rice mill, washed with distilled water to remove dirt and other impurity, then dried at room temperature for 24 hours. This given husk heated in a muffle furnace for 2 hours at 600 degrees Celsius. Then got this ash. This is figure 2 shows the rice husk ash. After apply green chemistry route method, which we'll discuss further, then got this powder silica. It was used as a reinforcement in composite. Then the matrix material used in the present study was copper, which is 99.8% pure with 85 volume percent used in composite. Last one is magnesium powder. It was used as a wetting agent with high volume percent throughout the process. And this is the green route method. This is the synthesis process of microstructural silica. So this is the rice husk ash. This is the rice husk. This is the rice husk ash. Then this is 8 gram of rice husk ash was taken in a beaker and stirred in a 100 ml of 3 normal sodium hydroxide solution. In this solution add, and it was heated in covered beaker for 1 hour by stirring constantly. And the resultant solution was filtered out and allowed to cool down at room temperature. And then the 5 molar sulfuric acid was added in a previous solution under control condition until the pH 8.5 was obtained. This solution settled for 24 hours. Then precipitated silica was obtained. This precipitated dried at 50 degrees Celsius for 4 hours in the oven, and then got this powder silica. So fabrication process used in this study is powder metallurgy. This process we'll see in three part: powder, processing, and properties. Powder can be blending through ball miller with required size and shape. Then the characterization takes place. Then this method processing generally consists of three basic steps: compaction, sintering, hot processing. Compaction is generally performed at room temperature. Sintering is usually conducted at atmospheric pressure, and then hot pressing is the process of compacting metal powder in a die. Then after compaction, powder material are heated in a controlled atmosphere in a process known as sintering. Most important part is result and discussion. The structural property of powder silica was examined by XRD. Figure 6 shows that XRD pattern of powder silica. Then this is the highest intense peak in the graph. This peak is obtained in between 30 to 35 degree. Similarly, figure 7 shows the XRD pattern of copper silica magnesium composite. This result shows transform tetraconal symmetry into orthorhombic symmetry, and highest intense peak obtained in between 40 to 45, that is exact value is 45 degrees. The second characterization technique is energy dispersive X-ray spectroscopy, that is ADX. This table shows the elemental analysis of copper, silica, magnesium composite and silica. So column 1 shows elements silica, oxygen, magnesium, copper, carbon, sulfur. So total impurity present in copper, magnesium, silica is 99.70% and total purity present in silica is 78.76%. One more point I want to discuss here, that is prepared silica is oxidized. EDX result indicate presence of oxygen, that is the transformation of silica as a silicon oxide. Then third characterization technique is SCM, scanning electron microscopy. This micrograph shows the surface morphology of given sample, that is silica. So figure A shows that stone-shaped particle, whereas figure D found diffuse particle. Similarly, the second micrograph of copper, silica, magnesium composite, this figure shows residual pores distributed within the pores. This figure also shows silica is a highly porous material and this copper have broken up during thermal decomposition of organic matter. Magnesium was used to avoid a highly porous structure. This is the prepared copper metal matrix composite. I want to conclude few points in above study is crystalline silica has been successfully prepared by using green chemistry routes. This is the economic raw material. Rice husk ash was used. The XRD shows that silica prepare has characteristic crystalline phase with an average crystalline size of about 40 micrometer. This silica shows microflake and irregular rod-shaped morphology with agglomeration as confirmed by SEM analysis. And then the third one, EDX result confirmed the presence of silica in the form of silicon dioxide. In general, these characteristics can be used as a production of metal matrix composite with reinforcement crystalline silica powder form and economic raw material for industrial and wide-scale application. So the copper metal matrix composite material are characterized by very good structural property. Copper composite material reinforced with silica found porous structure. It is a very useful property for application in the electronic industry. And on the other hand, the production cost of composite material are higher than those of conventional materials, and these costs have been compensated for during their services. Then the main production method of metal ceramic based composite material is powder metallurgy method. We are pledged to acknowledge funding agency, that is UGC-DAE CSR. This research work is funded by UGC-DAE Consortium for Scientific Research Indore. All the experimental work related to material characterization using XRD, SCM and ADX is carried out at UGC-DAE CSR Research Labs, India. And authors are also thankful to Dr. Mukul Gupta, scientist of UGC-DAE CSR Institute, who is a collaborator for this project also. These are a few publications which I have referred in this study. Thank you, dear audience, for listening this presentation.
Okay, we thank you. We thank the speakers for this nice presentation and video. Unfortunately, we don't have an opportunity to ask questions, but it was a very informative and very broad subject. And our next speaker is not available as far as I know. I just want to ask if there is anybody who is in the list and present in participants. I think we don't have anybody. Let me check. Next speaker is Irshad Hussein. We have not yet, he has not contacted or he is not in the list yet. We don't know if he's trying to connect. And the next available video at the moment is just a minute.
Hello.
Yeliz Güleşçi Kartal. I'll do my best to just a minute. Okay. Our next presentation is from Yeliz Güleşçi Kartal, so number 65. Give you brief information about affiliations. Right. She's from Gazi University, Physics Department, Ankara, Turkey. And the subject of, or the title of the presentation is the electronic, magnetic, and half metallic properties of new titanium titanium rutile full titanium rutyl. I don't know what it is. Full Hössler compound and ab initio investigations. Briefly, some modeling. Let's listen to this presentation.
Hello, my name is Yeliz Güleşçi Kartal from Gazi University. I am glad to be here with you today. I'd like to talk to you about Hössler compounds. One of them are studied with time-2 thallium compound. The electronic, magnetic, and half metallic properties of new time-2 thallium Hössler compound and ab initio investigation. The first definition of the half metallic Hössler compound was presented with the nickel manganese antimony compound called half Hössler in 1983 by Wood et al. In the half metallic material, while one of the bonds has metallic character, the other one shows semiconductor nature around the Fermi energy level. The reason why half metallic materials have become popular in the last quarter century is that these materials are functional in new spintronic and magnetoelectric devices. Fusar alloys include two types, namely high Fusar alloys with a stoichiometric composition XYZ and full Fusar alloys with a stoichiometric composition X2YZ. Here, X and Y belong to transition elements, while Z is SB element. While for the full Fusar alloys X2YZ, there are two structures. One of them is the copper to manganese aluminum crystal structure, which is the space group name 225. The second is the mercury to copper titanium crystal structure, which is the space group name 216. Electronic and magnetic property research studies for many titanium 2-based modular compounds were previously carried out. Additionally, the electronic and magnetic properties of some other compounds were studied in various studies. Even though some other alloys were investigated for their electronic and magnetic properties by theoretically and experimentally, there are no any studies on the titanium 2-titanium compound until now. In present study, the electronic and magnetic properties of titanium 2-titanium compound was studied firstly. The calculations of the titanium 2-titanium compound were performed by using the Vienna-Benicius simulation package. The electronic and magnetic attributes of compound titanium 2-titanium have been used for principal calculations based on EFT. Vienna-Benicius simulation package. The first principal code was induce to compute the total energy. This code employs DFT within the projective argumented play method. The projective argumented play method describes the interaction between the ions and electrons, and the exchange correlation is treated within the generalized gradient approximation formulated by the Perdue and Anzapov. First, we will choose atoms of titanium 2-titanium compound from periodic table in VAS. Figure 1 shows that the crystal structure of titanium 2-titanium compound in 216 phase group. The cell parameters belonging to the atoms of titanium 2-titanium compound were recorded in the second step. Compute the total energy for both structure and density from the properties of the compound. Projective argument of the method describes the interaction between the ions and electrons, and the exchange correlation is treated within the generalized gradient approximation by the calculated for the parametric state of the material. So let's multiply of the bulk model, equilibrium, energy, and volume values of the titanium 2-titanium compound are given in table 1. Examining figure 2, the highest contributions from titanium 1, titanium 2, and lutetium elements were provided by the d orbitals, and the highest contribution from the titanium element came from the p orbital. The contribution of electrons to the total density is greatest around the Fermi energy level represented by the zero energy point. On the other hand, it was observed that the peak density decreases as it moves away from the Fermi level. In the distant energy region, it can be argued that the electron contribution to the total state density was very small. The necessary calculations were made to observe how much contribution comes from the which element at an orbital level to the total and atomic contribution of titanium 2-titanium compound. The spin up and spin down mass structures of our compound were given in figure 3. Bulk calculations were made to support the density of states of our compound and to show the bulk gaps more clearly. While the snap state of titanium 2-titanium compound cut the Fermi energy level, there was an energy gap observed in spin-down structure. Therefore, while the spin-up band structure of titanium 2-titanium compound in 260 space group was metallic. The downbound structure was semiconductor due to the energy gap obtained at the Fermi energy level. Of the orbital and the high contribution from the helium element came from the p orbital. The contribution of electrons to the total density is greatest around the Fermi energy level represented by the zero energy point. On the other hand, it was observed that the peak density decreases as it moves away from the Fermi level. In the distant energy region, it can be argued that the electron contribution to the total state density was very small. The necessary calculations were made to observe how much contribution comes from the which element at an orbital level to the total and atomic contribution of time-2 thallium compounds. And spin-down bar structures of our compounds are given in figure 3. Bond calculations were made to support the density of states of our compounds and to show the bond gaps more clearly. While the snap state of time-2 thallium compound cut the Fermi energy level, there was an energy gap observed in spin-down structure. Therefore, while the spin-up bond structure of time-2 thallium compound in 260 space group was metallic, the down-bond structure was semiconductor due to the energy gap obtained at the Fermi energy level. The total bond gap was calculated as 0.382 electron volts. This energy gap showed that time-2 thallium compound was a half metallic ferromagnet. The total magnetic moment value was found to be 1 4 magneton per formula unit. It was seen that the main contribution to the total magnetic moment of time-2 thallium compound was provided to the titanium-1 atom. Finally, these metallic and semiconducting spin states show that time-2 thallium precursor compound, the half metal ferromagnet with 1 4 magneton per formula unit magnetic moment, time-2 thallium precursor compounds can be new candidate material for using in speedrunning application. Thank you.
Okay, just a minute. The owner of this presentation is with us. If there's any questions you want to ask about the research, you can ask your questions. But I'll ask one question. That is, which program did you use? Which software did you use? I couldn't understand that part. Hangi program kullandınız?
WASP. We have got WASP program. MDA.
Oh, MDA. Okay. Okay. I don't know if there's any other question, but so what is the effect? What is the name? Sorry, I'm just trying to understand the importance of ab initio or molecular modeling. Is this the first stage for molecular modeling, or is this the first stage for atomic simulation, which part of it actually goes to this ab initio studies? Ab initio çalışmaları moleküler modellemenin parçası mı yoksa atomik modellemenin parçası mı?
Ab initio hesaplamaları soruyu doğru mu anladım? Moleküler modellemenin bir parçası mı dediniz? Atomik
Evet.
modellemenin mi?
Yani çünkü molekülerde dediğimiz zaman when we talk about molecular modeling, we talk about something different. But when we say atomic modeling, it's slightly different than molecular modeling because atomic modeling, you're talking about a group of similar atoms. But with molecular modeling, you're talking about a group of different atoms. Atomik modellemede biraz daha çok aynı tür atomlardan bahsederken, diğerinde ise birden fazla tür atomlar üzerinde ne yapmış oluyoruz? Bir modelleme yapmış oluyoruz. Ab initio bunların temelini mi oluşturuyor? Neresine tam olarak geliyor?
Hocam zannediyorum ki moleküler kısımlar. Çünkü bizim burada aynı benzer ya da farklı atom hesabı yapma gibi bir kastımız yok. Atomlarımızı periyodik tablodan seçerken tamamen kendi kişisel tercihimizle belirliyoruz. Burada bizim bildiğimiz tek şey var. Atomik pozisyonların yerleri, X ve Y atomlarının geçiş metali olduğunu biliyoruz. Z elementinin ise 3A ve 6A grubu elementlerinden seçildiğini biliyoruz. Bu aralıkta atomlarımızı seçip kendi kişisel tercihimize göre bir bileşik oluşturup bu bileşik üzerinden hesaplamalarımızı gerçekleştiriyoruz.
So what you're doing, let me explain this in English. You're designing your molecular system with the desired atoms of your choice. Then the positions of atoms in the lattice is important parameter in this case. So you're basically by choosing different atoms, you're modeling atomic calculations based on their lattice positions. Is that correct?
Yes, we know that X and Y atoms are translation metal. Z atom 3A and 6A group elements.
Okay. Any other questions? If you want to join with the questions, you're more than welcome. Otherwise, I will thank Yelis for nice presentation and information that she has given us. Do you have any other information regarding this molecular modeling? So when you have ab initio modeling, what is the next step? Can you give us some information? Ab initio'dan sonraki aşama nedir genellikle? Ondan sonra hangi aşamaya geçiyorsunuz? Ab initio yaptıktan sonra bu sadece burada bitiyor mu? Yani bu
now we have got only WAS program, but we want to buy different package in the future and try another types of computing like phonon calculations.
Okay, you're going more into detail, I guess.
Yes.
So you're not talking about macro scale. You're talking about submicron scale, I guess. So what is the advantage of going submicron scale instead of macro scale?
We know Ozlar compound is using spintronic and magnetoelectric devices, and we choose this compound as it has not been studied before.
So for magnetic properties, we don't need macro properties, I guess. We need submicron properties. So in order to change these, modify these properties, submicron species are important in terms of magnetic and other properties. Thank you very much. Thank you, Yeliz. Thank you. I think this is it. I cannot. Let me see. Just a minute. Let me check my list of people who will act as speakers. Let me ask the audience again if there is anybody who wants, who is in this hall to act as speaker. Otherwise, I will say thank you again to Yeliz.
Sorry, I interrupt you. May I ask one question? To ask a question for the Yeliz, but
you're more than welcome.
Thank you very much. Thank you very much. First of all, I would like to apologize from you, Yeliz, because you are the scientist in this area, but I am a little bit away from your area. But I would like to try to question. I'm sure that you compare your work with directly relevant one or other different studies. So when you look at the comparing of the other studies with your paper, how can evaluate your study result is much give the future of your area, or you can improve? Am I explain?
How can you improve your results? She's asking.
Thank you very much.
How do you decide to improve your results when you look at your study? So this is the study I'm going to do in next 10 years, and how do you decide of properties to improve in your area of expertise?
What is your innovation view for your studies?
That's a very good question.
Thank you very much.
Hocam çalışmamızın getireceği yeniliklerden bahsetmemi mi? Hani neye öncülük edecek bu çalışma gibi? Doğru mu anladım soruyu bilemiyorum.
Yani öyle de değerlendirebilirsin veya sen çalışmanla bilimsel dünyada bu branşta şu inovasyonu katacağım ya da bunu geliştirirsem bilime şu katkılarım olacak. Bu diğer çalışmalardan farklı şunu koydum dediğin unsur nedir? Onu sormak istedim. Soru sormak için özür diliyorum tekrar.
Teşekkür ederim hocam. Sağ olun. Ben de yayına tesadüfen bağlandığım için heyecanlıyım. Kusura bakmayın.
Bağlantı bugün bugün zorluyor bağlantı.
Bu şekilde daha az heyecanlı olursunuz. I believe you will be less anxious at this moment, but we are listening to you.
We know with this study, the time-to-time compounds, magnetic and electronic properties. Furthermore, we know Husserl compounds are easy to obtain experimentally and theoretically. Also, their atomic position are clear.
Okay. Peki şöyle diyelim. Siz Türkçe açıklayın. Ben ara sıra çevirmeye çalışayım.
Şimdi şöyle, Husserl bileşiklerinin yarı metalik ve ferromanyetik özelliklere sahip olması gerektiğini biliyoruz. Bizim de bu bileşikte aradığımız özellik buydu. Spin-up ve spin-down band yapılarına bakarak bileşiğin hangi karakterde olduğunu analiz etmekti bizim hedefimiz ve bu bileşiğin spin-up'larının metalik, spin-down'larının yarı metalik özelliğe sahip olduğunu ve bileşiğin karakteri hakkındaki detayları elde etmiş olduk bu programdaki elektronik ve manyetik hesaplamaları yaparak. Yani bir nevi bu bileşiğin karakter özelliklerini sergilemiş olduk. Biliyoruz ki senkronik cihazlarda ve manyeto-elektrik cihazlarda kullanılan bileşikler bu bileşikler. Bu özelliklerinden faydalanılarak cihaz yapımlarında
to utilize these compounds in electronic equipments, you have decided to work on these magnetic and electronic properties of these materials because they are more compatible for these purposes. Then you can change the properties by doing ab initio modeling and see which properties changes at what rate as well. Yani bu çalışmayla beraber hangi özellikler nasıl değiştiğini tespit ederek aslında uygulamaya uygun olup olmadığını ne yapmış oluyorsunuz? Test etmiş oluyorsunuz.
Evet.
Peki diyelim ki bir tane şey seçeceksiniz. Bu çalışmayı bitirdiniz, sonuna kadar gittiniz. Yeni bir çalışma seçmek istiyorsunuz. Ab initio'da bunu modellemek istiyorsunuz. Hangi özelliğine ilk önce bakıyorsunuz? When you want to model a certain compounds or certain alloy systems, which properties would appeal to you? Yani size hangi özellikler daha ilginç geliyor olabilir? Elektronik, manyetik, elektronik artı manyetik artı çok daha farklı özellikler. Genelde yapabileceğiniz şeylere mi bakıyorsunuz yoksa uygulamayı dikkate alarak mı yapmaya çalışıyorsunuz?
Şöyle, bize verdiği sonuçlara göre hareket etmeye çalışıyoruz. Başlangıçta bir beklentimiz var. Toplam manyetik momentinin sabit bir değer olması örneğin. Yani toplam bir manyetik momente sahip olması, bir bileşiğe ait bir bant boşluğunun olması ki bu bize yarı metalik özelliği olduğunu gösteriyor. Manyetik ve elektronik özelliklerine birlikte bakmak bileşik için daha doğru bir hareket diye düşünüyorum.
Anladım. Evet, teşekkür ederiz. Şöyle bir soru daha sorayım o zaman. Bu hazır sizi bulmuşken ab initio'da çalışmalara benzer başka çalışmalar var mı? Bu bileşik için değil, genel olarak ab initio'la beraber yan yana giden başka şeyler var mı? Programlar veya
Hocam, bizim
modeller?
aynen. Mesela elektronik ve manyetik hesaplamalar konusunda kullanılan VN2K programı var diye biliyorum. Hani şu an elimizde sadece WASP var ama bu hesaplamaları yapan ama daha uzun sürede WASP'ın bizi hızlandırdığı bu. Kısa sürede daha kısa sürede sonuçları, dataları ele alabiliyoruz.
Anladım. WASP'ı kullanabiliyoruz diyorsunuz.
Evet.
Tamam. Çok teşekkür ederim. Yeliz Hanım'a her şey için. Sizi bayağı bir yorduk bugün. Ama en azından aklımızdaki bazı soruları da bu şekilde sormuş olduk. Grupta bu salonda sunumu olan başka arkadaşımız var mı acaba veya hocamız? Yok galiba. Bakalım. Evet, hepinize çok teşekkür ediyorum. Şu anda bir Hakan Bey'e sormak lazım. Acaba elimizde başka video var mı diye müsaade ederseniz onu bir sorayım. Evet. Normalde bu süreç içerisinde arada olması gereken sunumlar var. Belki o sunumlara katılmak isteyenler gelebilir. Onları da bu arada beklemek istiyorum. E, Şu ana kadar sunum yapan arkadaşlara çok teşekkür ediyorum. E,
Hocam, eğer mümkünse bir ara vererek diğer tarafta biraz bakıp sonra katılımcı olursa size dönmemiz bir ayıp olur mu ayrılsak? Peki. Peki, çok teşekkür ederim.
Kesinlikle olmaz. Ben de kaydı durdurup 5 dakika ara vereceğim.
Çok teşekkür ederim.
Teşekkür ederim. Teşekkür ederim. Sağ olun.
Sayın hocam,
Evet.
ne yapıyoruz Sayın hocam?
Yani şu anda kimse yok şeyde.
Tamam. Gelecek
Şey
var mı hocam?
kaydı durdurdum efendim.
Gelecek var mı?
Yani şu anda ondan üçüncüyü çaldık.
Tamam. Şu anda YouTube'da izleniyor zaten şu anda ama tamam biz bekleyelim isterseniz hocam birazcık daha.
Bekleyelim.
Tamam.
Sıkıntı yok.
Evet. Tamam Sayın.
Sıkıntı yok.
YouTube'da yayın devam ediyor. Ona yapacak bir şeyim yok şu anda. Durduramıyorum
Yok.
onu hocam. Tamam Sayın hocam.
Tabii şey değil, kapatmıyorum.
Tamam Sayın
Gelen
hocam.
olursa takip ediyorum zaten.
Tamam Sayın hocam.
Hemen
Teşekkür ediyorum.
oynatacağım. Tamam. Veya sözü vereceğim.
Tamam.
Tamam, oldu. Merhaba hocam, hoş geldiniz.
Merhaba.
2 dakika sonra başlayabilir miyiz? Sizin için mahsur olur mu?
Hay hay.
Hemen geliyorum.
Hazır videoyu mu kullanacaksınız yoksa ben canlı mı anlatayım?
Sizin videonuz yok şeyde, benim
Gönderdim
listede.
ben. Öyle mi?
Evet. Canlı
Kaydetmeyi
anlatırsanız
yapmıştım ama.
sevinirim. Yani bana gönderilen şeyde, ya sistemde sadece 3 tane video vardı. Sizin
Ha.
videonuz yoktu.
Tamam, ben o zaman buradan sunumu açıp share screen yapacağım, anlatacağım, öyle mi?
Evet, aynen öyle hocam. Aynen
Tamam.
öyle.
Ne zaman derseniz başlayalım o zaman.
Tamam, bir dakika lütfen.
Hay hay, tamam.
Beklediğiniz için teşekkür ederim. Hocam sununuza istediğiniz zaman başlayabilirsiniz. Biz hazırız.
Ekranı açtım. Ha. Şimdi mi? Nereden yapacağım?
Share screen'den ekranınızda şey görünecektir.
Benim sunum.
Sunumunuz. Önce sunumunuzu açıyorsunuz.
Tamam.
Evet. Tamam.
Geldi. Tamam.
Geldi, evet.
Hello, I'd like to welcome all of you to this afternoon session of this international conference. In this presentation, I'm going to talk about the investigation of vibration damping properties of polyanthracene silicon oil dispersions, which is a part of my PhD student Gökçe Çalış study. Carried out in Gazi University Chemistry Department, Smart Materials Research Lab. I will talk about electrorheology definition and the aim of the study, and the synthesis and characterization of polyanthracene will be given. And then we will focus on the electrorheology, dielectric and vibration damping characteristics of polyanthracene silicon oil dispersion system. And then we will finish with conclusions. Okay. Electrorheology is the science deals with the flow of materials under various external forces, such as electric field. If electric field is applied to dispersions, this is called electrorheology. If magnetic field is applied to the dispersions, it is called magnetorheology. Before applying external electric field, particles are dispersed with high entropy. After applying electric field, these upper and lower electrodes, they are aligned. The particles are aligned between the electrodes, and we apply force. One of these electrodes, for example, upper electrode, to break this chain structure, and it resists to this force, and we measure this as shear stress, and then we go to viscosity. This was video. As you see in this video, particles are randomly dispersed. Now they are aligned between the electrodes when electric field is applied. Okay. This is the system. In our lab, we measure electrorheological behavior of fluids. This is electrorheometer, this is cooler, this is heater, and this is external electric field supplier. The aim of this study was to investigate the electric field induced vibration damping characteristics of polyanthracene silicon oil dispersions. Polyanthracene is seen on the screen. It has conjugated p bonds after the application of electric field. The hoping of p electrons provide the conduction in the whole system. We have compared these polyanthracene particles with previously reported polyanthracene quinone molecules. They are similar to each other, and we will discuss the results of both. We synthesized polyanthracene starting with anthracene by using iron trichloride as an oxidant at 150 degrees Celsius and subjected to FTIR analysis to characterize the chemical structure, and we observed that expected bondings are taken place. And then we carried out characterizations of polyanthracene particles by using dynamic light scattering. We measured their average particle sizes as 0.6 micrometers, and their surface charges are also important. We measured their surface charges by zeta potential measurements as plus 19 millivolts. It means when dispersed in insulating medium, these particles will repel each other and stay suspended in the dispersion. And then we measured the conductivity of these particles, and we found that it is 10 to minus 4 Siemens per centimeters, which is well in the range of electrorheological studies, which requires conductivity of particles between 10 to minus 8 and 10 to minus 4 Siemens per centimeters. And then we measured the electrorheological response of polyanthracene silicon oil dispersions. First of all, we applied no electric field, and then we applied various electric field strengths. When we applied electric field strength, shear stress suddenly increased, and then we removed the electric field. The stress sent back to the original volume. So these experiments indicated that polyanthracene silicon oil system is a smart system which can understand the presence of external electric field when it is applied or removed. So we call it smart fluid. If you look at the video on the left-hand side, after the application of electric field, particles start aligning between the electrodes. And from these experiments, we have decided that 20 mass per volume percent concentration is optimum. That is why rest of the experiments carried out with 20% concentration. Yes, as you see, we apply shearing force to distort the situation, distort the chain structure. And then we measured the change of viscosity with shear rate. First of all, we applied no electric field, and then we applied various electric fields, and we observed that viscosity, electric field induced viscosity abruptly increases and show shear thinning non-Newtonian viscose behavior. Then we measured the shear stress of polyanthracene silicon oil dispersions by applying shear rate and measuring shear stress. But these shear stress are measured under various electric field strengths. We observed that as the electric field strength is increased despite increasing shear rate, shear stresses increase. It shows that this is not Newtonian fluid. It doesn't show Newtonian flow behavior. So we checked the system whether it shows Bingham type flow behavior or not. And we did fitting for Bingham flow. It didn't obey the Bingham flow. Then we applied CCJ model, as you see the equation on the screen, and it fits to this CCJ model, and we explained the results according to this model. From these curves, we calculated the dynamic yield stresses and graph against electric field strength. From the slope of this graph, we decide the type of mechanism, electroyogical mechanism. If this slope is 1.5, it obeys to the conduction model. If the slope is equals to 2, it obeys to the polarization model. So it was 1.5. So we concluded that the mechanism, electroyogical mechanism, obeys the conduction model. And then we pass to ER response of polyanthracene and silicon dispersions by calculating electroyogical efficiency, which is the yield stress difference between electric field applied yield stress and zero electric field stress, yield stress divided by zero electric field yield stress, and it was calculated as 81 Pascal under 3 kV per millimeter. The previously reported polyanthracene quinone radicals ER efficiency was 24. So polyanthracene is much better than polyanthracene quinone radical reported in the literature. It is more useful for industrial applications. Dielectric properties are important for these kind of smart materials. That's why we examined the change in dielectric constant of dispersed particles with frequency by using constant concentration and electric field. We obtained these experimental curves, and then we carried out fitting of these curves to Cole model, which obeyed this model. And from these graph, we calculated dielectric constant difference. It is the difference between epsilon naught and epsilon infinity. Epsilon naught is the dielectric constant at low frequencies, and epsilon infinity is the dielectric constant at high frequencies. And this was 3.7 for polyanthracene, our new material. It was 0.8 for the previously reported polyanthracene quinone radical. As the delta epsilon dash increases, the material becomes much better for electrological applications. We want delta epsilon dash big, but we desire small lambda, which is the relaxation time. And we calculated the relaxation time, change of relaxation time with frequency. And from this equation, we calculated that relaxation time of polyanthracene was 0.51 seconds, whereas polyanthracene quinone radical was reported to be 2.75 10 to minus 4 seconds. This is very good for polyanthracene quinone radical. It responds to the electric field and goes back to the original state in a very short period of time when compared to polyanthracene. And then we checked how does elasticity modulus of these dispersions change with shear stress under various electric field strengths. We observed that elasticity modulus remains constant until a definite shear stress, and then the fluid system, dispersion system collapses. From these collapsing points, we calculated the critical stresses and graphed against electric field. But before the collapsing points, we determined the linear viscoelastic region in which elasticity modulus does not collapse. Elasticity modulus goes linear. So in this region, we carried out the rest of the experiments in the linear viscoelastic region. For example, we carried out creep recovery tests in this linear viscoelastic region before the collapsing. Here you see the change of elasticity modulus and viscous modulus with frequency. We observed that elasticity modulus of these dispersions are bigger than the viscous modulus. It means these dispersions can store the frequency or the distortion applied from external forces and can be used as a vibration damper. As you see on the video, after the application of electric field between upper and lower plates, fibers or fibrils are formed, and when the frequency is applied, they keep their chain-like structure. And it indicates that elasticity modulus is dominant to the viscous modulus, which is a desired property. In this graph, you see the change of elasticity modulus with time, because this is important from industrial points of view. We expect no change on the elasticity modulus in time. So when electric field is applied in the linear viscoelastic region, elasticity modulus remains under various electric field strengths. When there is no electric field, elasticity modulus changes and behaves like Newtonian material. But when electric field is applied, the material is non-Newtonian. And then we carried out creep recovery experiments to this polyanthracene silicone oil system. In the first part, we applied 2 Pascal stress to the system and applied, measured the time versus strain. You see material behave like an elastic material, and then we removed the force applied in here, there you see the arrow, and we observed the recovery of the system. Here, elastic recovery, and then viscous deformation in here. From the underneath of the graph, we calculated the percentage recovery. As you see from the table, percentage recovery increases with increasing electric field strength. It shows that the system is a smart system and shows high recovery after deformation. So it is suitable for industrial vibration damping applications. In conclusion, here in the video you see that, let's go to let's go to the beginning. Here you see a washing machine. It vibrates during spinning. It vibrates. When we give electric field to the vibration damper, the vibration of the washing machine decreases. So the fluid works as a vibration damper. So we can say that to the best of our knowledge, the vibration damping properties of polyanthracene and quinol radical and polyanthracene have not been reported yet. And the experimental results in this study shows that polyanthracene silicone oil dispersion system can be more promising material for industrial vibration damping applications. And this study was supported by Gazi University Research Fund. And I would like to thank you for your participation and for your attention. And I'd like to thank the organizing committee for giving us to this opportunity. Thank you. If there is any question, I'd like to answer.
Okay, if there's any questions from anybody, from our guests, you're more than welcome to ask questions about the topic that Professor Ali Ibrahim Inal mentioned. But I have one question, if you don't mind. When you have this liquid or these particles inside the liquid,
yes,
they are naturally forming this fibrous structure, isn't it?
Yes.
Yes.
As a result of conduction, they are electric conductive particles.
Electric conductive. Is there any? So let me ask this way: what is the effect of this solution? Is there any limitations of this solution that you use to align these particles?
Particle size is important. The type of base fluid is important, and type of particle is important. It has to be electrically conductive and small and resistive against aggregation.
Aggregation. The base liquid. Why is it important? And does it have to be conductive?
It has to be particle, non-conductive. It has to be electrically conductive and small and resistive against aggregation.
Okay.
Because we expect the conductivity as a result of particles, not due to the base fluid.
Base fluid. Base fluid doesn't have to be conductive.
Yes, otherwise it makes a breakdown.
Okay. Oh, all right. I see. Why is the particle size important?
To protect against agglomeration.
So you cannot work with particles that have nano size, or
we do.
Is it better?
Between few microns to nanometers.
Okay. All right. Okay. Thank you very much again for your presentation. It was a lovely presentation.
Thank you for your sharing. Thank you.
Is there anybody who is in the list and who wants to do their presentation, his or her presentation? Let me see. Right. Is it possible to call Fatih Buyrul or Alper İncesu or Yavuz Emre Yağcı or İsmail Hakkı Kara if you are present in the list, because I can see two people with unknown, Onur Okur, and user. Maybe user is one of these speakers. If you are one of them, please raise your hand. Otherwise I'll give a break for 5 minutes. Hocam çok teşekkür ederiz tekrar.
Hoşça kalın, görüşmek üzere.
Görüşmek üzere.
Hoşça kalın.
Merhaba Onur Bey, hazır mısınız?
Evet hocam.
Okay, our next guest is Onur Okur. Our presentation was about investigation on producibility and mechanical properties of aramid reinforced composites built with titanium diborite. Originally, Fatih Buyrul was supposed to be present, but I think he's not available. And in place of Fatih Buyrul, Okan Okur will present this study. Now we are listening to Onur Okur. Stage is yours.
Professor, actually, Fatih is absent, and I made a video recording in the name of him.
Okay. Do you want to play? Do you want to play that?
Yeah, I will share it now.
Okay then.
Hello, dear audience. Today, I would like to make a presentation about our recent study. It is entitled An Investigation on Producibility and Mechanical Properties of Aramid Reinforced Composite Filled with Titanium Diborite. The content is production of aramid composites. I would like to talk about experimental procedure and results, and then finally conclusion. How did we produce composite? We produced composite by using vacuum infusion technique. It is really cheap, cost efficient, easy to fabricate. It is well used for production of the polymer matrix composites. And as you can see, there is a schematic figure of the technique, vacuum infusion technique. There is resin inlet, a vacuum outlet, resin distribution media, peel ply, and vacuum bag. Vacuum outlet lets you to suck all the air in the bag, and resin lets us, the resin inlet lets allows us to
İyi, kestik geldik.
breathe all resin into the vacuum bag, and there is vacuum net here, peel ply, the aramid fabrics that we want to produce, and on top of all there is a vacuum bag, and around this vacuum bag, this media was enclosed by using sealant tape. Here it is aramid fabric that we use for the production, and epoxy resin and hardener that we use, and also we use stamped boride as a filling material. First, appropriate amount of epoxy resin and stamped boride powder were mixed by using ultrasonic cleaning machine for 30 minutes. The weight percentage of the epoxy resin is 80%, and hardener is 20% weight percent. First, after peel ply laid over on the plate, as you can see, we placed 8 successive layers of aramid fabric over and over. The orientation, we choose 2 different orientations, which are 45-degree and 90-degree. As you can see, there are 8 layers of aramid fabric, and on the top of last aramid fabric, we then again place peel ply on the fabric, and on top of it again we place vacuum net. On the top of all, the vacuum bag was placed. The vacuum line and resin inlets were also placed in the vacuum bag. As you can see, these sealant tape can be seen here. This is the line that sucks resin into vacuum bag, and this is the vacuum outlet that lets air in the bag out and pulls the resin out, excessive resin out. This vacuum, this negative pressure provides an homogeneous distribution of resin filler mixture. The vacuum pump ran for 4 hours, and after 4 hours, the pump stopped, and vacuum bag setup was left for curing for another 24 hours at room temperature. This is another sample that we produced. After 24 hours, we removed all peel ply, vacuum net, and we took the aramid reinforced composites, as you can see in figure. After removing the aramid composites, the post-curing process was applied at 120 Celsius degree for 4 hours. After curing process, the samples from the composite laminates were cut by using water jet. Now I would like to talk about results and experimental procedure. After cutting samples, we carried out some SEM images, SEM analysis, porosity test, bending test, impact test, and tensile test. Now you can see some images of the aramid composites. A, C, and E, as you can see, A, C, and E B and C, that are the composites stacked at 45 degree orientation, and D, E, and F are the composites, produced composites stacked at 90 degree. As you can see, these are the composites without styrene filler. B and E are the SEM images of one person consist of 1% filling styrene filling materials. C and F are the composites filling 4% weight percent of titanium boride. We obtained that from the images that A and D has small porosity. As filling materials increases from 1 to 4, you can see the spaces between fabrics increase. Another test we did during the study, it is porosity test. As you can see, these blue bars are 45 degree orientation. Composites has 45 degree orientation. Black bars are the composites stacked at 90 degree. you can see the difference between 1% between the material composites having 1% titanium boride and without titanium boride for 2 and 4%. The porosity of 1%, the composite have 1%, had the lower porosity. The other test we did was the tensile strength test, tensile test. As you can see, this is the aramid composite stacked at orientation of 45 degree. These results, the results are close each other, but you can see titanium boride filling material can enhance the elongation, maximum elongation, and this is the other result. This is the other result of the composite stack at 90 degree. You can see the yield strength of the composite increase significantly. This is the black one is without stamped boride, and 2% and 4%. It can be seen that it enhance the mechanical tensile strength of the composites. This is the bending test. As you can see, bending test results, the bending strength of the materials can increase by increasing at time the boride filling material. This is the without time the boride. You can see 45 degree orientation and 90 degree orientation. Generally, it increases the bending strength of the composites compared to composites, aramid composites without stamped boride filling material. And again, this is the short hardness of the composites stack at both orientation 45 and 90 degrees. You can see that the aramid composite having the 1% stamped boride performed slightly better compared to other composites. This is the impact toughness of the composite stack at 45 and 90 degrees. Here, both composites stack at 90 degrees and 45 degree had performed nearly the same in a same manner, but as you can see, the composites stack at 90 degrees had the higher results compared to that of the composites stacked at 45 degree. But generally, they perform similarly. When it comes to conclusion, it can be concluded that the proper amount of standard boride filling material can enhance the mechanical properties. It also improve the elongation of the composite. Another observation we obtained was that 1% standard boride filler enhanced the bendability between epoxy and aramid. Findings also show that 1% standard boride filler proportion can enhance the yield strength of composites. Exceeding values 1% can cause an increase in porosity. Therefore, it affected the mechanical properties negatively. Finally, the aramid composite stack at 90 degrees showed better properties compared to composite stack at 45 degrees. Thank you for your time and patience.
Thank you very much for the presentation. Will you be able to answer any questions, or Onur?
Yes.
Can we ask any questions? Will you be able to answer any questions?
Yeah.
One simple question.
Okay.
You have results from 45 degrees and 90 degrees orientation. I think it was strength. Is it? Must be one of them. It was strength. The difference between 45 degrees and 90 degrees was less in 2%, and I think it's the next.
This one?
Yes. So you can see the difference between 2% and 4%, and also 1%. They're not too away from each other. That's one thing. But can you go one more to the right or left, bottom? Next slide, please. Let's see. Next slide. This one. It was one of the bars. 2%. No, not this one. Yeah, 1% is quite low strain material. I don't know why. You said porosity is important, isn't it?
One thing I forgot to mention that it is another thing that we need to take into consideration was agglomeration. We try to take under control the agglomeration by using ultrasound, but I believe that in some samples we couldn't take the control because in some samples we came across a great deal amount of agglomeration in specific areas. So I think that is why in some samples we couldn't reach the strength we expected.
Right. So preparation is very important in these materials. I guess you have to be careful when you're spreading out these between the layers. But how would you prevent this problem? How would you prevent this problem if you could? How would you prevent this problem if you could?
One thing, we should use smaller particles. I mean, like nanoscale, in a range of nanoscale, because in some articles we encountered that nanoparticles had homogeneous dispersion in resin.
Under ultrasonic force, I guess.
Yeah, another thing, Professor, maybe we should extend the duration of the ultrasound in ultrasonic machine.
That's possible, yeah. Okay, thank you very much for your talk. It was very nice. And our next guest is Alper İncesu. Let me just a minute. Very sorry. Number is I'm just trying to find the number.
9, I think.
69, does it?
59, I think.
59, I'm sorry. Just a minute.
Hello, everyone.
Yeah, hi. 59. I need to make a small introduction. Introduction, I'm sorry. So our next speaker is Alper İncesu. He is from Top Technical Sciences Vocational High School, from Karabük University, and he'll be presenting us comparison of biodegradability and mechanical properties of hot-rolled pure magnesium and magnesium alloys study. We are listening to you, and the stage is yours.
Thank you. I'm sharing my screen. Can you see my presentation?
Yes, we can see it.
Okay, I'm starting.
It's better. Okay.
Hello, everyone. I'm Alper İncesu. I'm assistant professor at Karabük University. Ali Güngör is my colleague in this study. Title of our study is Comparison of Biodegradability and Mechanical Properties of Hot-Rolled Pure Magnesium and Magnesium Alloys. This is my outline. In the introduction part, I will shortly introduce you with biomaterials and implants. Then I will talk about experimental procedures of the study. After that, I will give results of experimental part and do some discussions about them. Finally, I will finish my presentation with conclusion part. Let's begin with introduction part. Implants are materials that act as support for broken, damaged, or injured tissue, especially the bone tissue, until the healing of its complete. We can categorize implants into three categories: biodegradable metal alloys, non-degradable metal or composite implants, and natural and synthetic polyesters. Our study is focused on to the magnesium and its alloys. You can see on the figure 1 some implant materials that can be used in human body. Here is the real photograph of fractured bone plate produced by chromium cobalt alloy. It's non-degradable biomaterial. Why magnesium and its alloys as biomaterials? Because magnesium has some benefits as biomaterials or some positive aspects to be used in human body. These are low density, high specific strength, high damping capacity, machinability is easy for magnesium, and dimensional accuracy, stress shielding, biocompatibility, and degradation to be finishing its job after healing of the tissue is a very important benefit of magnesium and its alloys. With this, also magnesium has some drawbacks. These are elastic modulus, low elastic modulus, rapid and non-stable degradation of in non-stable degradation in human body or psychological conditions, and hydrogen evaluation. These are some drawbacks of magnesium and magnesium alloys. How can we solve these drawbacks? Allowing thermomechanical treatments and heat treatments are some solutions for these problems. Alloying, in our study, we use three alloying elements, calcium, zinc, and manganese. Effect of these alloying elements to the magnesium alloys can be shown like this. Calcium helps in refining the microstructure and improving strength and grip properties of magnesium due to the formation of the intermetallic phases. Zinc provides solid solution settling and aging settling effect. Zinc helps to overcome the harmful corrosive effect of iron and nickel impurities, thus improves the corrosion resistance of magnesium alloys. Manganese just improves the yield strength slightly in magnesium alloys. Its most important function is to improve the salt water resistance of magnesium alloys by removing iron and other heavy metal elements. Also, homogenization heat treatment applied in our study. So, effect of homogenization heat treatment is, in the process of smelting, the greater density difference between elements leads to segregation, which complicates deformation processing. Therefore, homogenization is an essential process before deformation that reduces the microsegregation and harmful effect of tectic structure during deformation, enhances the ability of the deformation, and strengthens the alloy for aging. Hot rolling. Hot rolling also is a very important procedure to get a more strength material. Original core are generally SKS materials have coarse grains in their structures. By hot rolling or thermomechanical treatments, these coarse grains can be become very smaller grains, finer grains by hot rolling. Plastic deformation applied to this part, and grains become elongated. Effect of the heat results in accelerated grains. Finally, little bit grains can be growth in new fine grain structures. If we summarize with the introduction section, aim of our study is to control the microstructure of magnesium by alloying, to obtain a regular and steady degradation rate by controlling the phases resulting from the alloying by heat treatment, also improving the mechanical and biodegradability properties of alloys as a result of alloying, heat treatment, and hot rolling. Let's go on with the materials and method parts. Two different magnesium, zinc, calcium, mangan, magnesium alloys, and pure magnesium as a reference material were produced by the gravity die casting method. Chemical composition of them were given in table 1. Homogenization heat treatment treated alloys were examined, and the results of them were published in our previous study. In this study, we just analyzed the alloys after hot rolling application. The rolling process was performed in a double rolling device with a 200 mm roller diameter at a speed of 20 RPM. All samples were subjected to the 10% deformation in each pass, and a total of 30% deformation was applied by 3 passes. The initial thickness of the samples is 4.5 mm. Before the first pass application, samples were heated to 400 degrees Celsius and allowed to stand at this temperature for 30 minutes. Between the passages, the samples were kept at 400 degrees Celsius and 10 minutes, and the next pass was applied. Microstructural differences before and after emerging corrosion tests observed by scanning electron microscope, tensile tests and hardness tests were applied to characterize the mechanical properties of the alloys. immersion corrosion test and electrochemical corrosion tests were applied to bring out the biodegradability performance of the materials. Here is, you can see the SAM micrograph of magnesium and ZXM. Short form of the alloys designation is ZXM 100 and ZXM 120 alloys. Depending on the alloying elements added in ZXM 100 and ZXM 120 alloys, a fine grain structure approximately five times finer than pure magnesium we observed from the SAM micrographs of the alloys. Therefore, it can be said that alloying elements are effective to refine the grain size of the pure magnesium. When microstructure of ZXM 100 and ZXM 120 alloys are compared, it's seen that a hollow structure is formed in ZXM 120 alloys. You can see hollow structure here. The reason for this is that the ZXM 120 alloy consists of a diverse eutectic phases containing magnesium to calcium phase. Since the zinc over calcium ratio is less than 1.2 atomic percent, since electrochemical potentials of the phase are as calcium 2, magnesium 6, zinc 3 phase higher than the alpha magnesium, and it is higher than the magnesium 2 calcium. The magnesium 2 calcium phase together with the grain boundaries reacted with the etchant during the etching and caused such a hollow structure. Here is the tensile test results of the samples and stress strain curve of the samples. Yield strength of the pure magnesium was improved by alloying about 64%. Yield strength of ZXM 120 alloy could not be measured because it was fractured before yield point. This can be attributed to the hollow-like structure observed in ZXM 120 alloy because it is reduced to strength of the material by creating stress concentration points. The fact that tensile strength is below even pure magnesium supports this argument. In case of ZXM 100 alloy, it was determined that yield and tensile strength of ZXM 100 alloy compared to the pure magnesium were improved, but its elongation was decreased. You can clearly see the difference between the elongation and tensile strengths. Also, we applied electrochemical and potentiodynamic corrosion tests to the samples. You can see the SAM micrographs of corroded surface of the samples after 48 hours immersion time. The order of the corrosion rates obtained from the electrochemical corrosion tests and the immersion corrosion test is consistent with each other. The ZXM 100 alloy has the lowest corrosion rate, while pure magnesium has the highest corrosion rate. Despite the increase in the amount of the added alloying elements in the ZXM 120 alloy, the reason for the increase in the corrosion rate compared to the ZXM 100 alloy can be the presence of magnesium to calcium phase in the structure. And this is the immersion corrosion time and corrosion rate graph of the samples. We can take data from 4 hours, 12 hours, 24 hours, and 46 hours. And also we get 8 hours measurement. It can be clearly observed that especially magnesium and ZXM 120 alloy shows to quite aggressive degradation up to about 12 hours. You can see here very aggressive degradation can be observed. This form of the degradation can be seen from the SAM images in figure 3. We observed previous SAM images after immersion. This very aggressive degradation can be observed here, but we cannot observe this like degradation. We can stretch from the silicium carbide paper here. And sorry. In the ZXM alloy, the regular degradation pattern and a very low rate of decomposition were observed during the entire immersion period from 4 hours up to 48 hours. As a result, hot rolled ZXM 100 alloy contains low proportion of alloying elements without magnesium to calcium phase in the structure meets the requirement in terms of both mechanical properties and biodegradability properties for fracture bomb plate material. Conclusion, in this study, pure magnesium, ZXM 100 and ZXM 120 alloy were produced by the gravity die casting method. Homogenization, heat treatment, and hot rolling were applied to the alloys. Hot rolling conditions were analyzed as comparatively, and the following results were obtained. ZXM 120 alloys has much lower tensile strength than pure magnesium and ZXM 100 alloys due to the magnesium 2 calcium phase in its structures. The hardness of the ZXM 120 alloy is the highest due to hardening effect of the increasing alloying elements. ZXM 100 alloy showed the lowest and stable corrosion rates over the immersion time. ZXM 100 alloy can be considered as biodegradable implant for fracture bomb plate material with its improved strength and biodegradability properties. Here is my references. Thanks for your listening. If you have any question, I would like to answer them.
Thank you very much to Alper for this nice presentation. Very interesting study on magnesium alloys. Since we don't have much magnesium resources in Turkey, this is and magnesium is not easy material to work with.
Yes.
And thank you very much for your presentation. Do you mind ask a question? If I ask a question, I was just wondering, in your table 4 or figure 3, can you go back to figure 3, please?
Of course.
Oh, thank you.
Yes.
The next one.
Okay, here.
Figure 3, yes, in this one. So you have this is corrosion test, isn't it?
Yes. Some images after 48-hour immersion corrosion.
Okay. In ZXM120, you have a corrosion rate of millimeter per year, isn't it? This the one at the bottom, isn't it?
Yeah.
The one at the bottom. Okay, right. I just want to be clear. Wanted to be clear on this one.
Okay.
It appeared that the one on the right seems to be Z, but it's not. So the A, the pure one, pure magnesium, isn't it? The one on the top on the left.
Of course.
So A,
So it's pure magnesium.
Pure magnesium.
ZXM 120, ZXM 100.
Okay. And can you go back one more slide? Not this one, I'm sorry, the other one. Ah, yeah, okay, this is the one. Very nice, thank you. So A and C, they have different corrosion rates, isn't it? I mean, we see them as different. And B is higher corrosion rate. Sorry, lower corrosion rate.
Yeah.
So B is better in this case.
Of course, no.
Okay. But do you think the effect, the corrosion rate effect, is because of these pores in image C? If there weren't these pores, do you think it would be better in terms of corrosion resistance?
Of course, because this pores comes from the magnesium 2 calcium phases degradation. So it degrades firstly before the other phases of especially alpha magnesium. So these pores becomes into the material structures.
Okay. Is there any way of getting rid of these or removing these defects in
of course,
ZXM120?
So we applied that and we get this like structures. Means that zinc over calcium ratio should be higher than 1.2 atomic percent. If you arrange the ratio like this, you can get like this structures.
Okay. So your average grain size is also increasing with 120, and well, 120 and 100 are almost same. So this, do you think this is the effect of those small particles, because they go down from 102 down to 21?
I don't think this phase not so much affects the grain sizes after hot rolling. As you see, it's very similar to each other, so we can accept them.
No, I was just wondering, because the first picture, pure magnesium, very large grains.
Of course.
And when you have these compounds, elements added, the refinement takes place. And I was just wondering, is it because of the additions, or is it because of heat treatment?
Especially alloying affects the grain sizes, but main aspects of this part of study is hot rolling. So if we look at the micrographs after hot rolling, it's very similar to each other.
Yeah, that's true. Yes. Okay. Thank you very much for your presentation. I was just wondering if there is anybody who wants to ask questions in our guest list. Or let me check if there's anybody who actually made any comments on YouTube. No, not yet. Okay, and we don't have any comments or questions. Thank you very much for your presentation.
It's your welcome. Thank you.
And say hello to your to Ali as well.
Okay.
Okay. Bye bye. Thank you. The next speaker, she did her presentation, and we'll be waiting for presentation starting at 18:15 by Yavuz Emre Yağcı and İsmail Hakkı Kara. We will accordingly, if they turn up, we will accordingly start again. We're giving a short break.
Sayın hocam. Şükrü hocam. Şükrü hocam.
Heh,
Hocam
açıyorum.
isterseniz oturumu kapatın Sayın hocam. Bu saate
Öyle
kadar
mi?
gelmemişse yazarımız gelmez diye düşünüyoruz artık.
Yani şöyle ki aslında iki tane daha şey var. Yani 18-15'te başlaması gerekiyordu. Birincisi. İkincisi de ben hemen bakayım. 18.45'te başlaması gerekiyor. Acaba
Kimse bağlanmadı hocam. Şu anda
evet,
yayın
bağlanmadılar.
açıkta
Doğru.
kalıyor. Onu nasıl yapabiliriz? Takdir sizin. Salon başkanı sizsiniz Sayın hocam.
Ya kaydetmiyorum, ben sadece bekliyorum.
Şu
Gelirlerse
anda YouTube'da açık Sayın hocam. YouTube'da herkes izliyor şu anda bizi.
tamam.
Tamam.
Yani bekleyebilirim.
Bekleyelim o
Benim için
zaman.
sıkıntı yok.
45'i bekleyeceğiz Sayın hocam o zaman.
Evet, 45'i
Tamam.
bekleyeceğiz.
Tamam Sayın hocam.
Eğer yine kimse gelmezse oturumu
Ben
kapatırız.
buradayım Sayın hocam. Devam ediyoruz. Teşekkür
Tamam.
ediyoruz izleyicilere de.
Teşekkür. Tabii. Oldu. Görüşmek üzere. Ersin hocam kapatıyorum şimdi. Işığı açabilir misin oğlum? Şöyle.
Hocam kapanışınızı yapın Sayın Hocam. Kapanışınızı
Tamam.
yapın, kapatalım Sayın Hocam.
Tamam, oldu hocam. Oldu. Kapanışı yapalım. Okay, for those visitors who were watching us, thank you for your attention and participation to our conference. And good evening to everybody. Thank you very much. Kapatıyorum.
Kapatın Sayın Hocam.